Sir, we will start soon. Just we are waiting for more participants. So they are joining. So within 2-5, we will start.
Okay.
So, thank you, sir.
Okay, so should we start now?
Yes, sir. Yes, ma'am. Please.
So welcome back, participants. Welcome to the third session of the Young Physicist Meet 2023. So in this session, we have two speakers, and this session will be chaired by Dr. Somnath Chatterjee. Dr. Somnath Chatterjee is a professor of our Department of Physics, Adamas University. He has done his PhD from Indian Institute of Technology, Kharagpur in material science. And his area of research is nanomaterials synthesis and characterization, photocatalytic activities, degradation of water pollutant, expired drug, etc. Also solar cell, inorganic and hybrid, graphene-based sensors, and many other nanoelectronics. He has a total number 150 publications, both national and international journals and conferences. And he has been the supervisor of one PhD student who was awarded the degree, and many other students are also under his supervision doing PhD now. So this session will be moderated. I am Dr. Shatarupa Vishaj, and this session will be moderated along with Dr. Diptashikha Das, who is also an assistant professor of our department, and Mr. Moyuk Shadhuka, technical associate of our department. So I would request Dr. Somnath Chatterjee to take over the session and conduct.
Good afternoon all. Thank you, Dr. Shatarupa, for a nice introduction. And I am not killing much time, and welcome all the participants for the third session of the day. And I'm just introduce the first speaker, Professor Swastik Mondal. He is the professor and senior principal scientist from Functional Materials and Devices Division, CSIR, Central Glass and Ceramic Research Institute, Kolkata. And he has ample of experiences, and he published lots of journal in SCI level and Scopus publications also. And he has basically working in the field of crystallography of periodic and aperiodic systems, and also spherical electron density analysis of structure, property, relationship. And today he will give us the topic, that is the history, contemporary applications and future aspects of X-ray diffraction technique. So welcome Dr. Swastik Mondal to the YPM 2023. And please, I'm just, you already shared the screen. Thank you, sir. Please start your speech.
Okay, thank you very much for the nice introduction. I would like to first thank the organizer to invite me for giving this talk, and to this young physicist. I'm obliged to do that. Okay, so thanks. I start. The history, contemporary application, and future aspects of X-ray diffraction technique. I gave this name, but actually it is almost impossible to touch all the aspects within 45 minutes. I will then do it just really touching, means only few slides will be on each things. Okay, so X-ray diffraction, I think I cannot see it. On top of it, there is a bar. Do you know how to minimize this? No. Anyway, so the history of X-ray diffraction, of course, starts with the discovery of X-rays by Röntgen in Germany. And this is the famous picture, this one on the right-hand side, which was claimed to be hand of our wife, but later on there was some controversies about it. But anyway, the thing is, it was one of the very first pictures taken by X-rays where people can see inside material. So the bone structure and a ring in the finger is visible here. So immediately after the discovery of X-rays, people understood that this is a new radiation which can be used to understand the inner side of material. And the first Nobel Prize in physics was given to Röntgen for his discovery. Within 10-15 years, people started to do kind of initial or primordial, you can say, X-ray diffraction experiments. So this is the very first X-ray diffraction experiments which was published. Before that, in lab level, they have done more, but which was published. That is the X-ray diffraction pattern from copper sulfate hydride crystal done by Knipping and von Laue in Germany. And this shows that though they have put a single beam on the copper sulfate crystal, but they found some spots. It looks quite bad, but in comparison to today's standard, but it was clear that the crystal was actually diffracting the X-rays. So I put this picture beside because all these discoveries eventually get them Nobel Prize. Okay, and immediately next year, father and son duo, William Henry and William Lawrence Bragg, discovered the famous equation 2d sin theta is equal to n lambda, so which is the basis of any diffraction pattern. So if this equation is met, this condition is met, then we'll get. Then I jump directly in 1952, 1953, from 2013 to 53, it's almost 40 years. In between, there are many things happened. I'm just not telling all those things here. For example, Ewald sphere construction was there, powder diffraction methodology was developed. But I'm saying this because this is something very important in the history of mankind, which was successfully solved by X-ray crystallography or X-ray diffraction technique. So this picture is a famous picture. It is called Photo 51. It was actually taken by Rosalind Franklin and his group and her group. But this picture was solved by two persons, and this is a diffraction pattern from the very building block of our body, that is DNA. So from here, what they found is this X pattern that corresponds to a helix. That is something which is spiraling. And then this diamond shape, these are indicating that there is a long molecule. So this helix is long. And then there are smear spacing that reveals that the structure is repetitive. That's why we are getting these smear things. But there, if you look, there are two lines are missing. So these two lines which are missing, they indicate that there are some interference. That actually indicate that it must be a helix. Otherwise, this cannot happen. If it is just a line chains which are going up in a helical pattern, and that's why it is happening. Okay, with this model was built by Watson and Crick, and they also got Nobel Prize, and she missed it, but the Photo 51 was her credit. Okay, now I again jump to 1982. This is not a X-ray diffraction pattern. This is a electron microscopy diffraction pattern or electron diffraction pattern, but with X-rays also one can have these kind of pictures. This is important because this discovery actually changed the very notion of crystallography. So initially, or even today, people are taught in lower grades that crystals are some kind of periodic arrangement of atoms. Periodic arrangement of atoms is a wrong concept. That was cleared by this kind of pictures. So periodic arrangement has some mathematics with it, and that mathematics says there cannot be any symmetry which is fivefold. That is fivefold rotation, for example. So 5, 10, these are forbidden symmetries. It is mathematically proven. If it is a periodic structure, one cannot, for example, in a periodic manner, one cannot fill a plane with pentagons. There must be some gaps. It is simply not possible mathematically. But this material, which shows this pattern, is not a periodic one, but it is giving discrete diffraction pattern. And actually, from there, they solved the structure as well. And this structure or this kind of material is called quasi-crystals, which is periodic, which is non-periodic, but ordered. Means if you know the basic structure, you can tell after 1 kilometer what will be the position of the next atom. But there is no repetition of anything. So basically, they do not have an unit cell. They have infinite unit cell. Okay, so IUCR, the governing body of crystallography of the world, has actually changed the definition of crystal from this diffraction pattern, that from strictly periodic, now it is any solid having essentially discrete diffraction diagram can be called a crystal. And Daniel Seckman was also given Nobel Prize. The discovery was in 1982, but he got Nobel Prize in 2011. So this is what I will cover in history. There are many more things that I did not show, but for that, probably I will need a lot of time. So I go to now, what are the types of diffraction that we generally use in day-to-day research work? There are primarily two different type of diffraction pattern techniques. One is single crystal diffraction, where there is a single crystal on which you put X-rays and you collect the diffraction pattern. And the other one is powder X-ray diffraction pattern, where you have many billions of tiny single crystal or crystal lights, from where you get a kind of ring pattern or powder pattern, 2D pattern. So there are other type of diffraction as well. For example, reference ring diffraction pattern or crystal truncation rod diffraction pattern. These are not used generally in day-to-day research things. So I will concentrate on these two different type of X-ray diffraction only: single crystal X-ray diffraction and powder X-ray diffraction. So what's the difference between these two? So in the left-hand side, this is the single crystal diffraction pattern, where you can see plenty of tiny dots. Remember, this is only one single image, and one can take multiple of these images, maybe 2,000 images, and then you can imagine the number of X-ray diffraction spots will be of the order of 1,000 or 10 to the power 3 or even 10 to the power 4, depending on how good your crystal is diffracting. Whereas in a powder diffraction pattern, the number of peaks drastically reduced to of the order of 10. It may be 20, 30, 50, 70, but that's all. That is all you have in your hand from a powder sample. But essentially, all this information that is there in the single crystal is also there. The only problem is three-dimensional data of single crystal diffraction is now projected into one dimension in the powder diffraction. And that's why the powder diffraction are very good in few things, for example, quick identification of phases and other thing. But if it is structure solution from powder diffraction data, where many numbers of information or data is required, that is extremely difficult. So ab initio structure solution from powder diffraction data is very difficult. So this is the difference between these two. Now I explain the difference again with some graphical display. That is, in a single crystal diffraction, we need a single crystal whose volume is of the order of 10 to the power 6 micrometer cube. So it's a big crystal. For example, the sugar crystal that we eat every day, if you see, those are the size of the crystal. And this is a diffraction pattern from the single crystal. Now, if I crush this single crystal to a very tiny crystal light, very tiny, that means of the order of volume is of the order of 10 to the power 1 micrometer cube, then essentially we'll get the same diffraction pattern. The only difference is the intensities that we'll receive will be very, very less. So if I go back again, this is the single crystal X-ray diffraction pattern, and this is the powder X-ray diffraction pattern. Powder or from one single crystal, one tiny single crystal, this is a pattern. Now, if you look at it, the orientation of the single crystal big one and the orientation of the small one is the same. Now, if I put another this tiny crystallite in a different orientation, for example, in a perpendicular orientation, we'll get again the same diffraction pattern, but it will be rotated by 90 degrees because it is rotated, the crystallite is rotated in 90 degrees from the previous one. Now, if I put another one in another random direction, then the diffraction pattern will get the same, but it will be it will be rotated by that random angle. If I put another one, it will be the same case. Now, if we continue putting, so let's say only 10 crystallites. Here, only 10 crystallites are there. But if you look at it, you will see that there is a ring kind of pattern is emerging. So if we put billions of these crystals randomly oriented, these tiny crystals, that is what is called powder, then what will we get? We'll get rings, complete rings. This is the powder diffraction pattern. So you look in any direction in this ring, it looks the same. But this is not the case for single crystal. For example, if I just superimpose these two from the single crystal data and the powder, you will find that all the single crystal spots has a line corresponding to it. But the only thing is it's a line, it's a ring. Every direction you get the same. But in single crystal, every direction is different. Okay. So what are the things that we could do with powder X-ray diffraction data? We could do structure solution, which is difficult, but it is possible. Radial refinement of crystalline materials, qualitative and quantitative phase analysis, microstructure analysis, texture analysis, phase transition studies. This is what physics people do primarily, phase transition studies by temperature changing or pressure changing and taking powder diffraction pattern and seeing how the peaks are shifting or splitting. So this is one possibility. And then studies of less ordered structures and structure of amorphous material. That is also possible by using pair distribution function. This is also terribly difficult task, but it is possible, and many more. So I will now show few examples of these problems that I have came across in my career with research on X-ray diffraction. So this is a vanadium complex whose single crystal could not be formed. This is another plus point of powder, that always you don't get single crystal. Particularly chemist people will know this, that many times it is really, really difficult to grow single crystal. In those cases, powder crystal is the only opportunity that you have to analyze the structure. This is a vanadium complex that I did, and this is the diffraction pattern and the final Rydberg plot. And you can see that this red line, which is basically the calculated from the model, matches very good with the diffraction pattern. And why this crystal was important? Because it has DNA cleavage activity. Yeah, so it was possible by using monochromatic powder X-ray diffraction data. If you do not have access to monochromatic powder diffraction data, then it is also possible with copper K alpha 1, K alpha 2, that is doublet data. But the things will be little more clumsy, but it is possible. Or in alternative way, one can go to synchrotron to collect the data or can collaborate. So these are the results. And if you can see that the R values are quite good, it is comparable actually with the single crystal data R values, what you get. This is the supramolecular architecture of this complex. Now, this is the second example. This is a praseodymium complex with tartrate. And here also we found a good match. This is also ab initio structure solution from powder diffraction data. And this is a final Rydberg plot. And one can see that it's matching very well. So any kind of this matching, this is also true for single crystal data, that what we try is to get as much matching as possible. So basically the R value that I told about, the closer to 0 it is, the better the structure are. In this case, it is 0.04, which should be considered for powder diffraction, ab initio powder diffraction, extremely good. If it is a single crystal, then extremely good, you can say if it is 0.01 or something. Okay. And this is again a supramolecular architecture of this praseodymium tartrate complex. Now, this is something different. This is not really a structure solution, but it was some alloys where what was the final structure that was supposed to be determined. So if you look carefully, all these peaks are matching except this one probably. Let's see. Sorry, this one. This one. There is this tiny peak. It doesn't look contributing much, but that will change the crystallographic symmetry of this material. So this is PM minus 3M. There are two phases. And this peak will be there for one of these phases. Here. Yeah. With these two phases, we could match, means for P, this should be there, and for F, this should not be there. This tiny peak is indicating that this P1 is actually very less in amount. It is only about 2%, but 2% of a different phase is also possible to identify from power diffraction data. So for example, if you are given a chunk of concrete and said that, tell me what are the things that is there, if there are some impurity of 2%, that you can also calculate from power diffraction data. And this is also not a very difficult task if you have a good quality data. Okay. This is just how the matching was in this case with one phase, the matching was like this, and with two phase, the matching was even better. That's what I showed. So the more good the match is, more accurate your model is. That's the idea. Now, this is a high entropy alloy, and here you can see that 1, 2, 3, 4, 5 different phases are there, and how beautifully this could be modeled. So if a sample has 5 phases or even more, this can be done quantitatively, that how much, what percentage it is by power diffraction data, which has a daily life or routine applications in many scientific applications. Well, this one is something different. That is, this is less ordered structure. You can see that this is not a diffraction or sharp peaks. These are some kind of structure is there in this red one, and also these are two different materials. And if you look carefully, that it is not a simple hump. There are some structure, and if you see this structure has some kind of bumpiness in them, it's a, you can consider these as a very broad peak. And these, I put 4 numbers corresponding to the D value, and if we match with the D value with the constituent material, what is inside, that matches with their full length, full molecular length, or multiple of that. So that indicates that it is though less ordered, but some kind of stacking is happening. And this stacking in which direction, you can say that the direction where it is the highest. So for the blue one, this is probably this about 4 angstrom different stacking. And for the red one, this is probably, these 3 are more or less equally present, but the multiple of it is less present. So this kind of orderness you can also find from power diffraction data. Now coming to single crystal X diffraction data. Structure solution, what are the things we can do? Structure solution and refinement of small molecules, this is quite easy, and nowadays it has become routine. If one has single crystal diffractometer and a software, one can do it by a few clicks. So it has become a routine job, unless until there is a problem like disorder or some other kind of problem. Study of hydrogen bonding and supramolecular architecture, study of structure property relationship, analysis of physical effects like absorption, anomalous scattering, phase transition studies. It is also possible with single crystal like powder crystal. Protein crystallography, this is very important because many of the drugs and others depends on their host proteins. Their activities depends on their host proteins, and that's why the structure of protein is very important. And this is an emerging field. Every day it is emerging, means it has a bright future. and then accurate charge density studies and many more. So I will now cover few of them, which I came across during. Few of them means I will. Okay, the structure solution thing I will not cover in single crystal because it is very easy nowadays, or very easy to do. And in powder diffraction, what I showed, essentially it is the same. Only difference is the number of data you have more, much more. So it becomes easier to do that. I will concentrate on charge density analysis, which is something a little difficult, but can be done using single crystal X-ray reflection data. So this was a problem that was brought to us, that this is alpha boron structure and this is beta boron structure. So these two was known already, and there is another polymorph of boron, that is amorphous boron. So amorphous boron, alpha boron, and beta boron, these were the three polymorphs known to us until 2007. And then in 2007, this came. This one was named gamma boron, alpha, beta, and then gamma. And this structure was not clear to all, because boron, in principle, boron is a mysterious element. It means it has 3 electrons, but it can make 4 bonds. So basically, it's an electron deficient bond, and that's why it makes unusual bonds. Like if you can see here, these clusters, these are made of only boron atoms. But why one element will make such cluster? Just to satisfy its electron needs with less number of electrons. So the structure was difficult, and we did quite a lot of research on alpha boron and gamma boron, and we found that these clusters that we showed, those are icosahedral clusters, they have some kind of orbital order in it. That is, from the corners of the cluster, always there are bonds going outwards. So if you look in this picture, these are the cluster, and if you see, always outward, the electron density is going. This picture is also true for alpha boron. Electron density is going outwards, so perpendicularly outwards from the cluster. The same basic building block of these two material are these icosahedral clusters, and in both cases, their behavior is the same. And then we did electron density studies. Electron density is nothing but instead of only solving the position of atoms, we also try to see how the electron density is distributed in the space inside the crystal. So in conventional structures, that is powder diffraction or single crystal, whatever, conventional structure are called independent atom models. There, we do not consider the charge transfer from one atom to the other atom because of bond formation or other things, intermolecular interaction like hydrogen bonds and others. But in principle, that should occur, and that is actually occurring, we have found. And from there, we could solve what's the crystal structure of the gamma boron was. And then another problem with the charge density was with boron carbide. So boron carbide, generally, we always say that it is B4C. But there is a paper where the paper title of the paper was The Invincibility of Disorder in Boron Carbide. This was a nice paper where they have shown that B4C is actually a wrong formula, because boron exists over a range of composition. So if it exists over a range of composition and equally thermodynamically stable, then one should not take only one formula of it, but they should mention about the range. So anyway, the single crystal that we could grow with boron carbide, we had to find that how exactly boron carbide is managing to make such unusual range of composition with one single structure. So basically, the structure remains same, only few atoms are being changed. So some carbon atom is being replaced by boron, or boron atom is replaced by carbon, and so on. And we found that there is a essentially boron carbide structure is similar to alpha boron. So there are B13 or B12 clusters, and these clusters are linked by a chain of atoms, 3 atoms, carbon, boron, carbon, and that's a structure. Now we found that actually this carbon, boron, carbon has a key there. So the central boron atom here in principle, it should have electrons here, but we found that there is no electron. So these pictures actually portray that, and there by these arrows we show that the lack of electron density in those places where the p orbital is, that indicates that that portion is devoid of electrons. So this portion is electronless. So if we put some kind of electron-rich material or like elements like carbon or something, that could give boron carbide electron here, and it will not change the structure because it can accommodate these extra electrons there. So that's the reason why it is found in a range of compositions. So I'm more or less close to the end of my talk. Now I will say something about the future aspects. So in principle, there are many things that is going on in a field of X-ray diffraction. But primarily, now the problem has arrived in a position that the X-ray sources that we have is basically either tube sources, copper or molybdenum, whatever that we use in laboratory, or rotating anode or something like this. And the other one is synchrotron sources. But these two is a limit so far we have. Is there any other possibility technologically to generate much more intense X-ray beam? The answer is X-ray free electron laser. So if you look at this picture, USA, European Union, European has actually two, then China, South Korea, and Japan. So developed nations, or who is emerging developed nations like China, they are now putting a lot of money. So one of these facilities takes millions of rupees, actually millions of dollars, to create those facilities, but they are pouring so much money. Why it is so? The reason is written down, also written here, that X-ray free electron lasers produce fully coherent ultra-bright femtosecond X-ray pulses. So far what I have shown was on continuous X-rays, not pulsed X-rays. So if this is pulsed X-rays, then what good it can do, because X-rays are actually giving an average structure, and that's the point. So if it is a pulsed laser, then probably we will not get average structures. We will get things see while it is moving. So for example, during a phase transition, if one can change the temperature and the phase is being changed, and every time if I'm sending this pulsed, then we can actually see the dynamics of the atoms, how they are moving, how everything is working there. Chemical reactions can be seen here, and to the accuracy of crystal structures, that is important. So experiments can be carried out in so-called diffraction before destruction mode. Why I wrote this? That is because if, in the first point, I should mention that the number of photons that we are getting is 10 to the power 11 to 10 to the power 12 photons. And that is actually billion times more than third generation synchrotrons. So that is huge amount of intensity. And that's why we can do this kind of intensity. If it falls on a protein, for example, the protein will be destructed for sure. Forget about protein, even hard materials, a diamond will be burnt. Then what's the plus point? But the diffraction will occur even before the diamond starts decaying, or the protein start decaying. So it is so fast, it's femtosecond pulse. So if I can push colored radiation, for example, white radiation or something, and just 1 femtosecond of exposure, that's it. That's all we need to do all kind of structural analysis for that protein. So basically nowadays in synchrotron center, one data collection takes about half an hour, and then it will take 1 femtosecond. Okay, for reproducibility and others, probably few seconds we will spend, but actually, essentially, it is no time. So experiments can be carried out in so-called diffraction before destruction mode. And then the other facility, like all synchrotrons, the X-ray wavelength is tunable. So you can have color wavelengths, means multiple wavelengths at a time, or you can also have monochromatic wavelengths, a particular wavelength at a time. And this advancement will made it possible that anomalous diffraction signals for identifying the phase problem in proteins, and then dynamic nature of protein at room temperature. All these kind of things can be done. Generally, the protein crystallography is done low temperature. In low temperature, the reason is in room temperature, protein crystal decays. But now what we can do, it decays, but with a time. Let's say it takes about 1 hour or 2 hours to decay. But if we can just put the protein in room temperature and immediately we collect the data within few seconds, then it's okay. Means at room temperature. Room temperature means at that temperature where body is functioning. So these are the plus points from technological advancements. This is the thing. And there are, of course, some other advancement or aspects that is going to become in future. So in single crystal or in powder crystal, we have a problem for ab initio structure solution. We call it phase problem. The thing is, in the X-rays are waves, and after diffraction, it has a phase part. And this phase part is actually lost during any experiment. So all that we have said that the model generation, this is basically nothing but finding the phases. This can be sorted out by reference beam diffraction experiments. That is another side, but these are conceptual. So, and I am not involved with this. I will now show two more future aspects that where I am involved. That is, one is dynamic electron density of material. What is that? So far what I have showed, except the last one, the powder diffraction structures and single crystal diffraction structures and so on, those were static densities. Static densities means we deconvolute the thermal part, or due to the thermal motion, the atoms are always vibrating. This vibration we subtract from the structure, and the rest structure we are saying that, okay, this is the position of the atom. But in principle, if you know Heisenberg uncertainty principle, we cannot fix a position of an atom. So we always have a uncertainty there, and this uncertainty plus thermal vibrations together makes another part that is called ADPs, or atomic displacement factor. So we generally deconvolute these two, and thermal parameter is called thermal parameter, and the rest of the electron density without thermal parameter is called static electron densities. This is an time average electron density study. Now, is it possible to introduce these thermal parameters again back to the static electron densities and see what is the thermal motion along with the electron density? So electron density which is dynamic, which is smeared over a region in this space. In principle, it is possible, and you can go through this paper. It was in Acta Crystallographica section A. It was already published in 2012, but still it is the first paper in this direction. So it will take another 10, 20, 30 years. I don't know how long it will take to be a more common research. But nonetheless, if you see in this picture, this is 20K data, that is static data. And this is 20K dynamic data. If you see these two, you will already see even at 20K, there are some differences, some smearing in these two electron density plots. And why it is important? This is important because temperature plays a crucial role in many of the properties of material. So a material show one kind of property at room temperature. The same material can show a different property at 200 degrees centigrade. The same material can show a different property at low side, means at minus 200 degrees centigrade. So temperature plays an important role in determining properties of material, and that's why the effect of temperature on electron density is very important. And now if I go to 100 Kelvin, then this is the structure and this is room temperature structure. Now look at room temperature structure and this 20K dynamic structure. 20K dynamic structure is essentially thermal vibration is not there. But Heisenberg uncertainty principle, or we call it 0 point vibration, that is there. So 0 point vibration is already close to static one, but within this range. So at room temperature, the electron density looks quite different from what it is shown in at very low temperature. So this can be this will be explored in future, and this is one aspect, the analysis of dynamic electron density. And then this is something which is now brewing. Actually, it is not published yet. It is unpublished data, but since it is already given in archive, so I can show these pictures. We say that X-ray diffraction gives us average picture of the bulk system, bulk material. Is it possible to analyze surface structure from X-ray diffraction? The answer is, in principle, yes, but in practical, so far nobody could do it. Why? Well, here there is a formula which says that the contribution of electron density, so in a given point, the electron density is a contribution from all the electron densities around it. So this can be found from this is green function basically. And so if we have a crystal structure, for example, this is boron carbide structure, and if we cut a plane there like this, can we say that what is there in this cut plane? So what is the electron density there? If we can remove all the contribution of these electron densities from the above plane, then in principle it should be possible. But during the talk, I mentioned once that in independent atom models or conventional models that we use for X-ray diffraction does not include any kind of charge transfer because of bond formation and others. So essentially, for independent atom model, you will get nothing. It will be exactly same. Here, the electron density will be exactly same as it is in the bulk. But now we are much more advanced, and we have a new idea, new concept with this concept is also not new actually. In 1980s, 1970s, from 1970s, it has started that can we consider the charge transfer of electron densities because of bond formation? And this is called aspherical electron density analysis. Aspherical means non-spherical. So independent atom model is spherical, where it is considered that the atom is sphere and it is making no interaction with other atoms, but it has a fixed position. But during 1970s, people started thinking that whether some of the electrons from one place is going to the other place and how the electron density in the space between the crystal structure is there. So how it looks like. So different model came on this, and the most common model considered that there are three parts of electron density. One is, of course, spherical core density. This is the red one. And the other is spherical valence density. This is the blue one. And then some part of these valence electrons are going to make bonds. For example, in this direction, if there is a bond, then this electron density will be concentrated more in this direction. This was not being considered in independent atom model, but in charge density model, we have this consideration. And there is a mathematical formulation also how we can model it using spherical harmonics. And if we can say that how the electron density is changing from one place to the other, then it is in principle possible. By the way, how much time do I have? I more or less consumed all my time. So in principle, if now we know the contribution of one electron to the others by this kind of aspherical electron density analysis, then in principle we can subtract these contributions and then we'll get the surface structure. So this is the very first example of these surface structures that is under review right now. And you see, this is the boron carbide, the same CBC bond. This is, and this are the, this one is surface and this one is the bulk. And you can see that there are simple differences in these two, and which are marked by red color. And the best thing about this is, if we can do this, if it is successful, then actually we can go a very accurate picture of surface structure. Very accurate means 10 to the power minus 2 angstrom. So far, the surface structure which is being published is of the order of angstrom. It will be 100 times more accurate than that. So I think that's all from my side. Thank you for your attention. Back to you.
Thank you, Dr. Mondal, for your very insight discussion on X-ray crystallography and X-ray diffraction. So, audience, I think we can ask some question to the presenter. Hello, participants. You have any questions, any queries? Because it is a very insightful discussion. Okay, sir.
Yeah.
I have some question that you are basically given a very good insight on X-ray, fundamentals of X-ray, then the phase analysis of high entropy alloys. And then you discussed something about the X-ray free electron laser, which is very new topic, I think, for
Yes.
the materials analysis.
Yes.
So here my query is when we can do it for the material synthesis, when we are doing the material synthesis, at that time we can take the X-ray, I mean the crystalline structures of the materials, the synthesized materials during the growth.
Yes.
But
So
here
basically, you can actually do the experiment during the growth, or even, for example, if you are dissolving sugar in water, you can see the steps how sugar is being dissolved in water. All the steps you can actually resolute. This is the beauty of free electron laser.
So because you are placing one quote that is diffraction before destruction.
Yeah.
So if our, I mean, my doubt is that suppose I have synthesized some nanomaterials, and after that, due to the high lasing system, maybe it will destruct our growth, or?
Oh, no. It's only the sample. Means if you are growing, you grow it separately. Just a tiny fraction of it you can put for the experiment. So the sample that you will put for experiment will be lost, will be destroyed for sure, because this is so intense peak X-rays. But you don't need to put all your sample for this experiment.
Okay. Okay, thank you, Dr. Mondal.
Yeah.
Madam, you have any question? Aparajita, madam?
It is very, very exciting talk and I enjoyed it. So nothing question, I enjoyed the talk. Yes.
So then again, clap for the good presentation, and thank you, Dr. Mondal, for your good presentation, and we learn a lot. Thank you, sir. Thank you, sir. So now, if there will be no question, then we can think about the new next presenter.
Hello, hi. I'm Navalita Dev. I am unable to share my screen. Yes, okay.
Okay, give me some time, ma'am. I will just introduce about you to the audience.
Okay, just I'm interrupting. Today we have one of very important guest with us, that is Dr. Sanjeev Ghosh, sir. Sir, am I audible?
Yes. Yes, Sanjeev. Yeah.
Maybe sir, right now he is not there. Okay. So I think we can go for the second person.
Sanjeev sir is here, I think.
Yes, he is here, but maybe at this moment he can hear us.
Okay.
So we can continue. Maybe later we can talk with him.
Okay. So Next speaker for today session is Dr. Navonita Dev from Indian Association of Cultivation for Science, Assistant Professor, School for Chemical Sciences. And she did her postdoc from University of Basel, Switzerland, Weizmann Institute of Science, Israel, and she did her PhD from University of Oxford, UK, and MSc from IIT Madras. So her topic is basically cold chemistry. So, however, I am very much not aware about this topic, and that's why I'm also excited to know what is cold chemistry means. So, ma'am, thank you for giving us the opportunity to hear something from you. So, please, if you may start, that will be better.
Yes, just a second. Can everyone see my screen?
Yes, yes, it is.
Okay. Thank you very much. Thank you very much, Professor Chetji, for introducing me for this kind introduction. I also thank Professor Dev, Professor Nyogi, Professor Das, and Professor Dhara for giving me this opportunity to talk about my research. Okay, so I will actually switch off my camera if that is okay, so that the internet connection is not slow. Okay, so today I will be talking about cold chemistry, right? So the way I have divided my talk is, can everyone hear me? I
Please,
am
please,
audible.
you are audible.
Go
You are
ahead.
audible.
Okay, sure. Thank you very much. So the way I have divided my talk is, so initially I will introduce this topic called chemistry or cold molecules. And I will briefly discuss what cold chemistry is. I will discuss what happens to molecules at this uh, at cold temperatures, as what the topic says. And then I will describe one experimental result, and I will give you some future direction. So I would like to mention here that I have joined IACS 1.5 years back. So, and I plan to set up a cold chemistry lab here. Okay, so let us first start with what is cold chemistry, right? So now the investigation of interactions of atoms and molecules and ions and molecules at near absolute zero. So we are talking about minus 273 Kelvin, as close to that as possible, because we cannot go there. So here, what a cold chemist does is we divide the temperature. So this is a log thermometer. What we see is that temperature from 10 Kelvin down to millikelvin, we refer to it as cold temperature. And temperatures below millikelvin down to microkelvin, nanokelvin, and further is referred to as ultra cold temperature, right? So now investigation of interactions of atoms and molecules at these temperature regime is cold chemistry. Now, with cold chemistry, researchers are able to get the first look at what exactly happens during the chemical reaction. Now, why do I say that? Okay. Okay. So when we are talking about this temperature, cold temperature, first let us spend some time to understand what happens to cold molecules at these temperatures. That is, we are taking molecules from room temperature down to millikelvin regime, right? To the cold temperature regime, 10 Kelvin and less. So what is happening is, now from a classical point of view, we can say that as the temperature is lowered, molecule starts moving more slowly, which means its velocity gets less, so its kinetic energy starts reducing. So that means at cold temperature, molecules have very less kinetic energy, which means potential energy starts dominating its energy description. Now, second, molecules are now spread over a narrower range of quantum states. Like, so what is it? What is the meaning of this? Means, so if you look at a rotational distribution of any molecule at room temperature, one can show that typically molecules will cover a wide range of rotational states. For example, hydrogen can easily cover until 30. So what it does is Boltzmann distribution of population distribution. So if we take a molecule and try to probe each state, we will end up with a Boltzmann distribution, right? So that means molecules at room temperature are occupying several quantum states, right? Now, this is different at cold temperature. Now this Boltzmann distribution will become narrower and narrower, and as we go down from 10 Kelvin down to millikelvin regime or even below, we will see that molecules are occupying like very few quantum states, right? Maybe one quantum state, right? That is a very particular state, we all know that. Now, the third point is, as we lower the temperature, the quantum nature in the atom molecular interactions are unveiled, which means that now atoms and molecules will collide with each other, but not as the classical ball model which we visualize inside our head, but here it will basically interact in a quantum manner that is basically it will be interaction of waves, right? So and therefore we will be able to unveil several quantum phenomena such as resonance, tunneling, quantum reflection. They all become observable not just in theory but experimentally, and we will see some experimental results in a moment, right? Okay, so now, okay, so that means these 3 points I said, that is unveiling of the quantum nature at low temperature, molecule losing its kinetic energy, and the molecules being spread over narrower range of quantum state, they all actually contribute in a very important thing, which is that it enables the very subtle features of the underlying potential energy surfaces to be probed. And if we really can go to that temperature where we establish these 3 effects, we will be able to experimentally probe even the minute subtle features on the potential energy surface. And what is basically a potential? It is the energy plotted with respect to some coordinate, usually the distance. Now, potential energy surface when plotted in one dimension is a potential energy curve. And if we have a detailed potential energy surface, we basically understand the mechanisms of every interaction. So this is a point we will keep in mind. But before that, let us first think what happens at room temperature. So what happens at room temperature? We all know that molecules collide. Classically, we will definitely say that Arrhenius equation is followed. K, which is your rate constant, is K, your rate constant will be given as A times e to the power minus EA by RT. And what we will see is if you plot reaction rate or reaction rate constant as a function of temperature, we will see that it increases with temperature. That means as you heat up the sample, the reaction rate will increase. Now the question is that can we extrapolate this curve, that Arrhenius equation, down to cold regime and replicate the behavior of the atoms and molecules? Now, the short answer is no, we can't. Now, the dynamics of molecular collisions at the cold, ultra-cold conditions are fundamentally very different from the transition state model, which is normally used to describe reactions with an activation barrier, the normal room temperature reactions, right? Now, because of the prevailing of the quantum nature at the room temperature and the other reasons like no quantum averaging out, that is the data that we get are not averaged over several quantum states, but is basically specific of some very specific quantum state. And of course, hello. Yes. So then what happens is the quantum behavior prevails at this temperature, and we see quantum effects such as resonance. So that means the short answer is that if we interpolate our K versus T Arrhenius equation down to cold temperature, we will not be able to replicate our behavior. Now, while conventional chemical wisdom tells us that the molecules are cooled down, all chemistry must grind to a halt. Now, recent experiments with cold molecules show that chemical reactions can be actually as fast as this cold, ultra cold temperature as they are at room temperature. Now, this is totally counterintuitive. It is very counterintuitive to what is happening. So now, before I go further, let us pause a while and revise de Broglie wavelength. So what is de Broglie wavelength? So what it is basically de Broglie wavelength lambda is given by H by mv. Mv is your momentum. And now what is generally observed is when the de Broglie wavelength becomes comparable to the intermolecular separations, then wave nature of particles can no longer be negligible. Okay. Now, what is happening is when we are lowering the temperature, our momentum is reducing, our lambda is increasing. Now, at low temperature, lambda, as soon as the lambda becomes greater than the intermolecular separations, quantum effect starts dominating the chemical dynamics, and we start seeing signature quantum effects such as quantum scattering resonances, orbiting, and shaped resonances, right? And so what happens at cold temperature? That is, we see that at cold temperature, so at 1 2 till some point the temperature reduces, but at very cold temperature, at when the collision energy, that is the collision temperature, is matches certain value, then what happens is there is a sudden spike in the reaction rate. These basically are resonances. These spikes in reaction rates are resonances. And here I show you one experimental data. This is done by the group of Professor Nerevicius, and it was published in Science in 2012, and it was one of the very first observation of resonances in reactive systems. Here they studied um, helium reaction with metastable helium and hydrogen, and they studied a penning ionization, right? Okay, so before I move on, so this is the experimental results, and we see clear peaks, which also matches with quantum theory calculations. Okay, so now what we can definitely say now is that because of the prevalence of quantum nature of interactions between atoms and molecules at cold temperature, simple extrapolation of experimental data obtained at higher temperature will fail to predict the behavior at cold and ultra cold temperature. Now, keeping this in mind, let us again take a pause. So what is basically happening? Let's see. So VR is our potential energy surface. Now, when atoms and molecules are coming close together, the angular momentum quantum number L, called the partial wave, which describes the collisional process, introduces a repulsive term given by h cross square L into L plus 1 by 2 mu r square. And this induces a change in the Schrodinger equation and adds these to VR. And what happens is that our V effective becomes VR plus the centrifugal repulsion term, which ends up introducing a small centrifugal barrier at the long range part of the potential, which is given by this region. Now, albeit this is a very small barrier, but keep in mind that we are talking of cold temperatures, 10 Kelvin and below, millikelvin, microkelvin temperature. And at those temperatures, the collision energy is not high enough. And this small centrifugal barrier should be able to keep the reactants separated and prevent from any interaction from happening, if we think about it. But interaction is taking place, just like I showed you an example in the previous slide, where we see not only interaction is happening, but tenfold increase in the reaction rate. Hence, what we see is that so that means interaction, if it is happening, so basically once what I show you here is that we scan with the collision energy, and when this collision energy matches this energy state, there is a spike in reaction rate. Now this reaction rate spike, this resonance can only happen if there is a quantum tunneling taking place. There is no other way, right? Okay, so now let us again go back to our cold chemistry topic. So when I say cold, I defined two temperature ranges. This is the log temperature again. We defined cold, we defined ultra cold. So temperature can be millikelvin, microkelvin, nanokelvin. Now the important question is, how cold should we go to study our reaction? Now, here the important thing to keep in mind is it is not about the temperature, but it is how many quantum states are participating in the collision study, and that should be minimum. Now, depending upon the system we are studying, for example, in this work, we are using supersonic beam experiment with neutral-neutral interactions. And for that, millikelvin temperature regime, like 10 Kelvin down to millikelvin regime, is already enough to show very interesting quantum effects. And that is what we will see shortly. Now, but even if we say millikelvin temperature regime, in order to achieve this temperature regime, we have to develop a completely new approach to experimental cold chemistry. So, because conventional methods might not be able to take the temperature to this regime, right? Now, I will show you what we do experimentally. And for that, I will be describing the results of an experiment which we did. So the objective of this experiment was determining the nature of quantum resonances by probing elastic and reactive scattering. So what we did was we took this system, that is we took metastable helium and we took D2. And then we will study two processes. One, elastic collisions. Elastic collision means that the energy before and after the collision will remain the same. And we will compare the result of the same with penning ionization. What is penning ionization? So when we have metastable helium, it is basically helium in an excited quantum state. Okay. Now, when this molecule is an excited quantum, it has excess energy. So when this collides with ground state D2, then what happens? The excess energy will be transferred, and the D2 will be ionized, and electron will be liberated from the process, right? So this is penning ionization. We will compare these two processes. Now, thinking about it, metastable helium and D2, okay, are same species. So maybe we will think that it should give similar kind of resonance processes, and let's see what happens, okay? Now, the way the experiment will take place, now the question is, how do we study the temperature in 10 Kelvin and down to millikelvin regime? Okay, we will do it with a variety of steps. The first steps being supersonic expansion. Now, what the supersonic expansion is, that we have a gas source on high pressure, and through a small narrow orifice, we release it into vacuum. Okay, adiabatic expansion takes place and it cools the internal degrees of freedom. Okay, now that comes at a cost. This cooling of the internal degrees of freedom, that it will actually go down to its low vibrational ground state, comes at a cost. The cost is that we look into this picture over here. So we start with this Boltzmann distribution. And after the supersonic expansion, it collapses to this very, very narrow distribution. So that means it is a very narrow distribution. That means it is occupying very few quantum states, preferably the low vibrational ground state, but it is very, very fast moving. In a moving frame of reference, the rotational temperature is actually very low, right? Now, the device we use is a very specialized valve, Corrigan-Lavie valve. It is pulsed and cooled by helium cryostat. It is developed by a scientist in Haifa Technion. No, Tel Aviv University, sorry about that, Tel Aviv University, and it's a patented product. He sells it, and he designed this valve, and many of the experiments in cold chemistry uses this kind of valve. What we get is the benefit of this valve is we get very high densities. Now we have cold beam that is definitely very narrow range of rotational or vibrational state, but in a moving frame of reference. How fast? The moving frame of reference is from 400 to 2000 meters per second, right? Now, the internal energy is definitely less than 1 Kelvin. Now, for example, for metastable helium, we have a dielectric barrier discharge placed directly in the nozzle, which further reduces the velocity spread. And actually, for metastable helium, the rotational state distribution may be as low as 250 microkelvin, right? But it is in a moving frame of reference. It is moving very, very fast, okay? Now, so now, how do we solve this now? So we solve this by moving into an inertial frame of reference. So that is, what we do is we take two beams. So one we have metastable helium and another we have D2. Both are moving very fast, few kilometers per second, 1 kilometer, 2 kilometers per second. But what we do is we merge the two beams. Here you have to compare the situations of two trains, head-on collision versus back-to-back collision, right? So if two trains are moving at 500 meters per second and they collide head-on versus they have a glancing back-to-back collision, then it is not the same. So here we basically go to the collision in a moving frame of reference. We were very fast, but we moved to an inertial frame by merging the two beams. Here, so traditionally the supersonic beam experiments are crossing at 90 degrees or 180 degrees, which makes the collision energy very high. But we play the tricks of merging it at 0 degrees, which takes the collision energy, which is defined by the relative velocity, down to very low temperature. But here a point to note is we will be able to vary the temperature by varying the supersonic beam velocities of the two beams. And we do so by cooling the valves by helium cryostat. And then the collision energy can be tuned from 300 Kelvin down to 10 millikelvin, right? Because even though when we match these two beams, V1 equal to V2, then it should become 0, but it doesn't become 0 because the valve has its own spread, spatial distribution, the temporal distribution, etc. Right? Okay. Now, so for penning ionization, what they did was they collided with metastable helium and D2 and varied the temperature from 300 Kelvin down to few millikelvin regime. And they detected the D2 plus, and they found that they got one resonance here. Okay, which is and then so this is a point we will keep in mind, that for penning ionization of this process, which is discussed in this paper, this is done by Professor Narvechu's group, and we will see that this is for penning ionization, they have one resonance. Okay, now since the potential energy is same, we might actually assume that even for elastic scattering it may be one resonance. Okay, now we will find out what we get. Okay, so for elastic scattering, ions are not formed, so we have to probe one of these two to probe the reaction. So what we end up probing this. What we do is we use a single photon near threshold ionization to probe the metastable helium, and we use VMI. Okay, I'll not go into the details of the slide, but I will tell you what VMI is briefly. So irrespective of where the particles are formed in space, where the ions are formed in space, if it has the same velocity component, then it will be focused onto the same point of the detector, right? So you see here we have three ions formed. Here we have the same theta1, that is the same velocity component. So that's why it forms on the same point of the detector. Now for this, the velocity component is different, but it has the same velocity magnitude. So it gets focused on another point, but they all form on the same ring. If the velocity is altogether different, then it will form a different ring. Now imagine this with balls colliding with each other and scattering away, right? So when this happens, then what happens is that the balls are hitting each other and then scattering in random direction. And now if you, with a VMI, you are focusing these scattered particles onto your detector. So a 3D ball to a 2D detector. So since ball scattering will form a sphere, then if you now eject this 3D sphere into a 2D detector, it should be a circle. What do we anticipate? We anticipate a circle like this, right? So we do
Excuse
this
me.
for Yes.
Excuse me, madam.
Yes.
Yeah, that time is.
Okay, I will wrap up in 2 minutes. Okay.
Yeah, please.
Okay. Yes.
Because we
So
have tight schedule.
yes. Okay. So what we see is that we get something like this. What is this? This is basically diffraction oscillation. It is basically happens because here the atoms and molecules at low temperature is behaving like waves and they are diffracting. Okay, these are basically interferences between different partial waves. So what we see here is the same VMI images which are formed at different collision energies. Okay, now what we see is that we get three different resonances. Okay, it follows all the classical features of resonances, that is enhancement of backward scattering at the peaks of resonances, right? Okay, so now what happens is that here when we compare, we see that for elastic scattering we have two new resonances, and this basically can be explained by knowing the mechanism of the resonance formation of resonances. So what we see here is for elastic scattering, both tunneling and quantum reflection is taking place. Okay. Now, but for penning ionization, the resonance that comes from quantum reflection do not take place because the penning ionization rate is given by the probability distribution times the autoionization function, which kills the probability, the quantum scattering probability, and only the tunneling occurs, right? So therefore, we show that the demonstrated two types of resonances and its mechanism of formations. Here we define two resonances orbiting, which is on or above barrier, which comes from quantum reflection. And the second type is shape, which is below barrier or quantum tunneling, right? Because of lack of time, I cannot show you future research interest. But if anybody is interested, especially students, please feel free to contact me. And my future research interest is long-term goal is studying astrochemically relevant reactions in low temperature regime, because such kind of cold processes take place in low temperature regime, and also studying the reactions at upper atmospheres. So because of lack of time, I could not explain it in a greater detail, but if any student is interested to know more detail, please get in touch with me. I will be very happy to explain it in greater detail.
Thank you, madam. Thank you for your insightful talk. And I think this is a new topic, in my opinion, also, because I know the nano, but I don't know about this cold chemistry. So it's really very interesting. And audiences, and before going to the question, Professor Sonjit Ghosh is joining with us. Sir, please, you say something about our this YPN 2023. Sir? Sir, your mic is mute, I think, sir.
Can you hear me?
Yes, sir.
Yeah. So Navonita, it's a nice talk, and Navonita actually is my student in Presidency College.
Yes.
So I'm glad that you are pursuing this kind of chemistry, which is very upcoming and new chemistry, and needs lots of things to be. If you want to set up in the lab, it needs a lot of things. So I'm very glad that you are doing this. And regarding this seminar, I always say that this is very nice for young researchers to collaborate among themselves and to give an idea of what kind of research is going on to the undergraduate and postgraduate students. And also, I think the faculty members of the department will be also benefited by this kind of lectures. So, Navonita, one question I have.
Yes, sure.
Can you see me?
Yes, I can see you, sir. Thank you very much for joining the talk.
Okay. So my question is, what is the ultimate goal of doing all this?
So first of all, we want to probe the potential energy surface. Other is we want to understand the very interesting reactions taking place in the interstellar medium and the upper atmosphere,
Okay.
which are necessarily taking place at very low temperature, cold temperature. And if we really want to understand how, and we know that trace elements of carbon, nitrogen, oxygen, everything, it occurs in space. So if they collide, possibly reaction is taking place, and possibly if they are at resonance, they're taking place very fast. So putting more light into how such reactions are taking place, understanding mechanism to the quantum detail. If we study reaction at low temperature, we will even be able to tell the subtle features of the potential energy surface, meaning we will be able to know the mechanisms of interaction to the very quantum detail, which gives us more controllability of a reaction.
Okay. Okay, thank you very much. And see you sometime.
Yes, I follow.
Okay.
Can I ask a question? Sir, Somnath sir, can you ask?
Yes, madam. Yes, madam.
Thank you, Dr. Dev, for your very interesting talk. Yes, you're really new to us. So I have only one question. When we are in the regime of so low temperature, the substance or materials behaves like some supers. I mean, superconductivity, superfluidity. So will this kind of things affect the reaction cross-section, or whether the reaction will be going on the same rate? Can you say something about this?
So basically what we are doing here is we have a molecule which are traveling very fast, and basically we are going to collision at temperature which are low temperature regime by merging, right? So that's why our cold collision energy reduces to millikelvin temperature, and because of supersonic expansion we have our rotational temperature which is very low nature. So with this we will be able to probe the mechanisms, quantum mechanisms of reactions at low temperature. And I don't think there is any link between the superconductivity or superfluidity at this point in the way the experiment is set up.
Millikelvin is very, very low temperature, because around 2.3 Kelvin we can see the superfluid nature of the helium. And all the character of the substances changes. So it may affect the reaction cross-section, the rate of reaction. And you have just shown that graph where there is sudden increase in the reaction rate. Can you
Yes.
explain why it is increasing? It is not a continuous increase, but you have some undulation there.
Yeah, so what basically happens is that when you vary the collision energy, when the collision energy matches with the resonance states, so then your phase shift becomes pi by 2. When the phase shift becomes pi by 2, then you have a sudden increase in the reaction rate. So, and only at that point that will happen. Now the broadening that you see are because of experimental limitations, because when we say we are moving at say 50 meters per second, we are not actually 50 meters per second, we are 50 meters plus minus something. So that's why we get the broadening basically. And also it is plotted in log scale. So this is what the resonance is. So what we are showing is that at very specific temperatures, where the collision energy is matching the resonant energy or energy levels, then there is a sudden increase in the reaction rate. And this, what we get experimentally, is exactly matches with the quantum scattering theory predictions.
Okay.
Yes.
So this is really interesting. We are in the domain when we are supposed to all molecules should be at rest, but they are having some vacuum energy, which causes the whole phenomenon, I think. So much more research have to be gone on this topic.
Yeah, this is very interesting.
Yeah.
Yes, very interesting field of
Yeah.
research. Yes.
Okay, thank you.
Thank you very much.
So thank you, madam, for your
you
talk. And I think participants should be benefited with your talk. And we have some lack of time. So thank you again. And we will conclude this session here. Thanks all.
Thank you very much.
Thanks all for joining us. Thank you.
Thank you.
Thank you, sir. Thank you, speakers, for such wonderful talk. And thank you, Professor Somnath Chatterjee, for chairing the session. Now we will move on to the next session. Dr. Deeptoshika Das will coordinate this session.
Good afternoon, all. I am Deeptoshika, and on behalf of my team, I would like to welcome you all in this today's seminar. And in this session, we have Dr. Purba Bhattacharya as our session chair and Dr. Papia Dhara as co-chair. Let me introduce them. Dr. Bhattacharya is an assistant professor in Department of Physics at Adams University. Her key research area is nuclear and high energy physics. Dr. Dhara is also an assistant professor in Department of Physics at Adams University. Her key research area is photonics and fiber optic sensor. I would request Dr. Bhattacharya and Dr. Dhara to take over the session.
Thank you, Dr. Das. Am I audible to all
Yes,
of you?
you are audible. Yeah.
Thank you. Thank you, Dr. Das, for this nice introduction. So good afternoon to all the invited speaker, respected professor, my fellow colleagues, and all the students who have joined. So without further delay, let's proceed with this session. And in this session, we have total 8 lectures. And we will start with the first one, which will be by Mr. Borishan Ghosh, a student from Hansraj College, Delhi University. And he will talk on thermodynamics observables and a strong magnetic field in the PNJL model. I will request Mr. Ghosh to please share your screen. Hello.
Hello.
Yeah,
Hello.
you are audible. You are
I'm
audible.
Okay.
Yeah. Please start.
Thanks a lot to Adams University for letting me present this presentation. And first of all, I'd like to thank my professor, Dr. Yogesh Kumar, and Mohammad Saif Khan, my senior, for introducing me to this incredibly interesting field. My topic for today's presentation is thermodynamics observables and the strong magnetic field in the PNJL model. So to begin, I would like to briefly lay out the roadmap for my talk. We will discuss what is QG. Can I just please give me 5 minutes? Okay. Okay, to begin, I will briefly lay out the roadmap for my talk. We will discuss what is QGP, what is the PNJL model, and how much of its complexity can be reduced by numerical approximations, its limitations, and we will conclude with the reference. So when we think of plasma, the first thing that comes to mind is, the fourth state of matter, that stuff on top of candles, ionized gas, where where the nucleus and the electrons move around each other in an unbound phase. Quark gluon plasma is something like that. We know that protons and neutrons consist of plasma, uh, and sorry, protons and neutrons consist of quarks, which are held together by gluons. So the quark gluon plasma is a state of matter in which all of these quarks and gluons exist in an unbound state, where they freely move around each other, and uh, and this process of freeing from this bound state, in that they exist in protons, neutrons, and other hadrons in general, are called deconfinement. To understand this process of deconfinement and its effects, there are various models that exist, like the MIT bag model, the phenomenological models, and the PNGL model. We would focus our study on the PNGL model mainly because of its mathematical rigor and its agreement with real life results. So if we draw out a phase diagram for all of these states of matter, we would see that at high temperature, at very high temperatures and pressure, we find quark gluon plasma. As we see in the top left corner of this graph, on this diagram, there is early universe. So at early universe, like just after the Big Bang, there was so much energy, there was so much temperature, and these, in these extreme conditions, we only found quark gluon plasma. And as the universe cooled down, it transitioned into the hadron gas. You find black boundaries all around, labeled first order phase transition. Now, what is this first order phase transition? A first order phase transition is essentially any phase transition that involves latent heat. Think of ice. When we supply heat to ice, after a certain point, it melts and converts into water. So there is a very clear distinction between the phases of ice and water. And such a distinction is found in this first order phase transition from an hadron gas to quark gluon plasma. Keep in mind that hadron, as we mentioned, are particles such as neutrons and protons. And quark gluon plasma is such a phase, but freely unbound state. And you would notice that at low chemical potential, mu equals 0, there is a dotted line, that is the crossover transition. At the critical temperatures near these dotted lines, it is very hard to distinguish, meaning it is almost, you cannot tell whether it is quark gluon plasma or a hadron gas. So at this fuzzy border at mu equals 0, we would primarily focus our study. So we begin with how we would rigorously treat such a model. The crux of the idea is deconfinement, where deconfinement is essentially a phase transition. And to understand that, we introduce a parameter that is phi, or the Polyakov loop. When critical temperature is reached, we start to transition into the state of matter that we know as quark gluon plasma. So at such a temperature, phi is non-zero. And as temperature approaches infinity, phi also approaches 1. Think of phi as a step function. We identify a state of matter as, like, if the phi is 1, it is likely we have quark gluon plasma at hand, and if phi is 0, we have hadron gas at hand. So when we put all of that together into our model and express that as a function of temperature, the number of flavors, the energy density, the mass of quark, and combine them into one equation, we see this. Here to the extreme left, you will see omega. Omega here is thermodynamic potential, which is analogous to psi, or wave function in quantum mechanics. It does not share its properties at all, but think of it as a fingerprint of the state of matter. Here you can find properties such as pressure, energy density, lattice constants from applying simple operators or deriving it directly from omega. Okay, so yeah, here omega is built out of other functions which we can express as phi, which is the chiral condensate or the Polyakov loops, and temperature. And these are the observables. Here, P is temperature, epsilon is energy density, and C are the lattice constants. Here, we can see that all of these constants derive their meaning from the thermodynamic potential. So how would we solve such a formidable looking equation? We can set the partials to 0, and then we will get a bunch of coupled differential equations. Solving those will get you nonlinear equations, and then solving for the nonlinear equation, getting a unified set of variables. We plug them back into the long formidable equation and get expression for thermodynamic potential with respect to temperature. And then we can go on and chart them into these graphs and examine the properties of the matter. There is a problem with this approach, is that there is no good general methods for solving systems of more than one nonlinear equation. This is a quote from the book Numerical Recipes, widely regarded as a standard for numerical analysis of this sort. So how do we tackle this problem? We make a simple model of thermodynamic potential with respect to temperature. We see that a lot of these complexities stems from phi, the Polyakov loop. And we already know that at high temperature regimes, phi approaches 1. So why not set phi equals 1 and see where this goes? When we set phi equals 1, most of the functions simplify, and we can see that most of these are just constants. Like most of these functions derive their value from constants such as the number of flavors, the energy density, and at the end, the integrals and the equations become quite trivial to solve. We treat the chiral condensate and Polyakov loops as constant, and our thermodynamic potential becomes a function of temperature and temperature alone. This makes solving the integrals somewhat easy. So once you do all of that mathematical manipulation, you end up with this almost linear looking equation where omega is A plus B with a function of T. F is a function of T, and A and B are scaling and like moving the graph up and down. And so you have a fingerprint of the function, and then you apply regression and get like a simulacrum of the original omega function that we had. And we figure out that A is A and B is such and such as described in the bottom of the slide. And then we see with varying temperature, how does fundamental constants like the thermodynamical observables that we were examining varies over temperature. Here, temperature, energy, pressure, all of these are scaled. Keep this in mind, and temperature is also scaled in terms of critical temperature. Remember, let's go back to the original graphs and compare this to our approximation. We see that there is incredible agreement with real life results. Now, we apply, we see how our approximated model fares in a magnetic field. We introduce the magnetic energy term in the standard energy equation, where EB is such and such, where N and S is the standard quantum numbers. We vary the magnetic field and study the effect of such a variable on the thermodynamic pressure. Here, thermodynamic pressure also falls out as a result of applying a few operators to thermodynamic potential. We also see what happens when we change the number of flavors of quarks. So we end up with this, and we immediately see what is the problem with this model is that at low temperature the data gets very noisy. Our approximation gets very noisy, but more or less the agreement with the result is still very impressive. At B equals 0 is the graph that we saw before, and it is reasonably close to the original equation. So let us go wrap up again. We had this huge equation. I don't even remember most of it, but as soon as we set the Polyakov loop, treat the chiral condensate as a constant, it reduces to an integral, and then we solve it using the standard methods, and then we end up with an approximation. And then once we introduce the magnetic field energy into the standard energy equation, we end up with this graph. So what are the limitations of such an approach? First of all, what we did was a very qualitative study of the phenomenon.
Just a minute, Mr. Ghosh. You have 2 more minutes. Okay.
We are nearing the end of the presentation anyway. So the limitation of this model is that there are, as I mentioned, at lower temperature regimes, our approximation gets very noisy. And we used a bunch of free parameters that we fitted to the real life data. We would expect that the free parameters would fall out of the first principles equations and not fitted to the real life, data. But this is to begin with a preliminary study of such equations, and this was a very enlightening experience to go through the study. I would present my references and open the floor for questions. Thank you very much.
Thank you, Mr. Ghosh. Thank you for this nice presentation and also within the time. So, any question to Mr. Ghosh? If not, then thanks the speaker. Once again, you got one message from Mr. Yogesh Kumar. Very nice presentation. So congratulations. Let's thank the speaker once again and let's move to the next speaker. The next talk will be by Dr. Porna Roy from Shohid Matongini Hazra Government General Degree College for Women, and she will present on interplay between finite availability and storage capacity in asymmetric exclusion process. Dr. Porna, are you there? Dr. Roy, am I audible to you? Your screen is visible, but you are not audible. Dr. Roy, your screen is visible, but you are not audible.
Hello, am I audible?
Yes, now you are audible.
Okay.
Please start. Hello, you are not audible once again.
Hello?
Hello, yes.
Yes, yes, I am starting this.
Okay, sure.
Yeah. Okay. So I am Porna Roy from Shohid Matongini Hazra Government General Degree College for Women. First, I would like to thank the organizers for giving me this opportunity to present my work here. So today I will talk about finite availability versus storage capacity in exclusion processes. This is the outline of my talk. First, I will give a brief introduction of what is an open tacit. Next, I will discuss tacit connected with a finite resource. Next, the basic principles of main field theory, which we have used in our model. Next, motivation and fundamental questions behind our model. Then I will describe our model, its results, and at last, summary and conclusion. Now, what is an open tacit? In a standard tacit with open boundaries, each side of a one-dimensional lattice is either empty or occupied by a single particle. Now, particles can enter the lattice from the left end at rate alpha, provided the first side is empty. It can jump to the right neighboring side, provided it is empty, and can leave the lattice from the right end at rate beta. So here the movement of particle is unidirectional and particles can hop only to empty sides. That means here each side can be occupied by at most one particle. This leads to a non-equilibrium steady state with a finite particle current in the tacit plane. Now for an open tacit, these two rates alpha and beta are constant, so that one may consider the tacit plane as being connected to a reservoir with infinitely large number of particles. Tacit has been exploited to model protein synthesis in biological systems, to describe quasi one-dimensional motion of molecular motors along microtubules in eukaryotic cells, and to describe different traffic flow models. Now this is the phase diagram for an open dataset. As we can see, there are three distinct phases. Low density phase, where mean particle density in the Tassel plane is less than half. High density phase, where mean density is greater than half. And in the maximal current phase, the mean particle density in the Tassel plane is equal to half. In this phase, the current is maximum in the Tassel channel. Now for alpha equals to beta less than equal to half, there exists another phase known as Hawk phase. This is basically a coexistence region of low density and high density phases separated by a domain wall or domain boundary. Now for an open tacit, the domain wall is a moving one which upon long time averaging appear as a inclined straight line. This is because of the uncorrelated entry and exit rates of an open tacit that has no strict particle number conservation. Now, here I have shown the schematic diagram of a tacit plane connected to a finite resource. So here the total number of particles, that is number of particles in the tacit plane plus the number of particles in the reservoir is constant. So here the entry rate alpha is not a constant, rather it depends on the number of particles in the reservoir at that moment. Alpha is basically a monotonically increasing function of number of particles in the reservoir. Now the reservoir is assumed to be of infinite capacity. So beta here remains unaffected or unchanged by the number of particles in the reservoir. Now the phase diagram of this model has exactly the same topology as an open tacit in the alpha beta plane. Only difference is that here the domain wall is a localized one, unlike the delocalized domain wall of an open tacit, because here particle number conservation yields a unique value of the position of domain wall. Now this is the basic principles of mean field theory. Here we have neglected all the spatial correlations, that is 2-point correlation function has been decoupled into the product of two 1-point functions. So the equation of motion for the density dni dt becomes rho I minus 1 into 1 minus rho I minus rho I into 1 minus rho I plus 1, where rho I is the mean particle density at the ith side of the tacit plane. But at the steady state, since d rho I dt equals to 0, so these two quantities, rho I minus 1 into 1 minus rho I and rho I into 1 minus rho I plus 1 are the same. Again, current in the ith side, Ji equals to rho I into 1 minus rho I plus 1. So these two quantities same. It means current is continuous in the tacit plane in the steady state. Next, motivations behind our model. Real systems are spatially extended with different regions which may act as storage or resources for the whole system. So there may be more than one reservoir in the system. This should lead to current between different parts of the system. Now, the strength of this current not only depend on the availability of the particles in the supply reservoir, but also it depends on the storage capacity of the particles in the receiving reservoir. In fact, it is the interplay between the availability and storage capacity of particles together with particle number conservation that control the non-equilibrium steady state in such systems. Now, this is our model. Here we have considered a system consisting of two particle reservoirs of equal finite capacity, R1 and R2, and they are connected by two tacit planes, T1 and T2, in an anti-parallel manner. T1 and T2 are of equal size. Now here, both the entry rate alpha and exit rate beta depend on the number of particles in the supply reservoir and receiving reservoir respectively. So here alpha 1 effective equals to alpha 1 f of n1, where n1 is the number of particles in reservoir R1, and alpha 2 effective equals to alpha 2 f of n2, where n2 is the number of particles in the reservoir R2. This f is a monotonically increasing function of the number of particles in the reservoir. Now, beta 1 effective, that means effective exit rate of particles from tacit plane T1 is equal to beta 1 G of N2, and beta 2 effective equals to beta 2 G of N1, where G is a monotonically decreasing function of the number of particles in the receiving reservoir. Here, N1 and N2 evolve dynamically. Now, in this system, total number of particles N1 plus N2 plus L into rho 1 plus L into rho 2 is a constant. Now, for simplicity, we have chosen alpha 1 equals to beta 2 equals to A and alpha 2 equals to beta 1 equals to B. So, our model reduces to a 3-parameter model, A, B, and mu, where mu is defined by NO divided by 12, where NO is the total number of particles in the system. So mu is basically a measure of the total number of particles in the system. We have chosen f of x equal to x by L and g of x equal to 1 minus x by L. Now, since the maximum value of f of x and g of x is equal to 1, so the maximum value of N1 and N2 is L. Also, maximum number of particles available in the two tacit plane is 12, which implies maximum number of particles available in the system is 4L. So, maximum value of mu equals to 2. So, at mu equals to 1, the system is in the half-fill state. Now, continuity of current in T1 and T2 implies two solutions for the density of tacit plane are possible. Either rho 1 equals to rho 2, that is the two tacit planes are in the same phase, or rho 1 equals to 1 minus rho 2, that is they are in the opposite phase. So the possible phases are LD-LD, that is both the tacit planes are in the low density phase. HD-HD, both of them are in the high density phase, both of them are in the maximal current phase, MC-MC. And LD-HD or HD-LD, that is one is in the low density phase and the other is in the high density phase. Now we have used mean field theory together with Monte Carlo simulations to identify the phases in tacits in the model parameter space AB for various values of mu and transitions among them. Now, since rho 1 equals to rho 2 or rho 1 equals to 1 minus rho 2, so phases are not uniquely determined by mean field theory. To uniquely determine the phases, we have to use minimal current principle. That means in case of multiple possibilities of phases in the same region of parameter space, the phase with minimum current will be the most stable phase. Suppose in a region, both the phases LD-LD and LD-HD are possible. Now, if we compute the current for these two phases, then we can see that current in the LD-HD phase is smaller than that in the LD-LD phase. So here, LD-HD phase would be the stable one. Next, here I have shown the phase diagrams for different values of mu in the AB plane. This is the result for mu equals to 1. This is for mu equals to 5 by 8 and mu equals to 7 by 8. Now, LD-HD or HD-LD, that is mixed phases, are possible only for values of mu greater than equals to 3 by 4 and less than equal to 5 by 4. Next, we have studied the nature of domain walls in the phase diagram. As we can see that here both localized domain wall and delocalized domain walls are possible. For example, along the transition between LD-LD and LD-HD phases, we can see that tacit T1 remains in the low density phase. There is only a density jump in the tacit plane T2. So here we will observe a single localized domain wall because here particle number conservation yields a unique value of the position of domain wall. Now, along the transition between LD-HD and HD-LD, since there is a density jump in both the tacit planes, we will observe a pair of delocalized domain wall. Because here particle number conservation yields a linear relationship between the position of the two domain walls without obtaining them explicitly. This is obvious because particle number conservation is maintained by shifting one localized domain wall in a particular direction and making a reverse shift or compensating shift of the second localized domain wall in the reverse direction. So there will be two delocalized domain bulbs, as we can see from this figure. Now we can see that for mu equals to 1, the delocalized domain will span the entire length of the tacet, where for other values of mu, the delocalized domain will does not span the entire length of the tacet. Because if we compute some meaningful theory, the mean position of the delocalized domain will, then we can see that for mu equals to 1, the mean position is equal to half. So it spans the entire length. And for mu not equals to 1, it does not span the entire length. Now, I will summarize. So here I have mapped the finite resource tacet model by two reservoirs, finite particle reservoirs connected by two antiparallel tacet lanes. Here current depends both on availability of resources at the supply side and storage capacity of the particles at the receiving side. Here the phase diagram is very different from the one-lane model, and we can see that dynamics here can control the steady-state spatial distribution of particles in the two reservoirs. Here the system exhibits both localized domain work and delocalized domain work. I would like to thank my collaborator, Astik Haldar, Professor Arvind Prey, and Professor Rohit Basu for their immense support throughout the work. And thank you.
Thank you, Dr. Roy, for this nice presentation. You have few questions. Let me read it for you. What is TASEP? Why totally? Why open TASEP? And what if we consider nearest neighbor approximation in MFT?
Okay. Open TASEP means it has no boundary. That is, when there is a closed TASEP, it is connected to a finite resource. That is, here the total number of particles will be constant. But in an open TASEP, there will be no boundary. So their total number of particles is not constant.
The next question is, what if we consider nearest neighbor approximation in MFT?
Nearest neighbor approximation is not well given. Here we have neglected all the spatial correlations. That is, we have decoupled the 2-point correlation functions, that means ni plus 1 into the product of two 1-point functions, that is ni average into ni plus 1 average. Okay, that is, there is no correlation between the two nearest neighbors.
Okay, thank you. And just one thing, he has also asked why totally in TASEP.
Totally, because here the particles, because here the movement of particle is unidirectional. Particles can move only to the right neighboring side. There is no movement to the left neighboring side. So here totally asymmetric. One jump is 1 and the other probability is 0.
Okay, thank you so much, Dr. Roy. I hope you got your answer, Mr. Arindam Basu. Is there any other questions from the participant? If not, then let's thank the speaker once again, and thank you for this nice presentation and also mentioning the time.
Thank you.
So,
thank you.
So let's move towards the next presentation, which will be by Dr. Yogesh Kumar from Hansraj College, University of Delhi. And he will talk about the expansion of QGP droplets in the presence of magnetic field. Dr. Kumar, are you there? Dr. Kumar, are you there? I don't.
Just before I saw him to come.
Yeah, actually, he was. Yes, he was
Yes,
there.
he was there. Maybe
we can move to the next participant actually. So the next talk, let's by Dr. Poonam Jain from Sri Aurobindo College, and she will talk about the applicability of VMI model in the determination of level structure. Dr. Jain, are you there?
Yes, ma'am.
Okay, so can you please share your screen and start the presentation?
Yeah, just give me a minute.
Sure.
It will take a time because I am on the tablet.
No problem.
Participants, attendance links for session 2 and 3 is available now in chat box. Please fill it up.
Dr. Jain, if it takes some time, actually, you can take
Is
your
my
time.
screen visible? Is my
Not
screen?
yet. Not yet.
Not yet.
Not
I
yet.
have already shared. I have already shared. It is taking time to be shared in the Zoom.
Not yet, ma'am.
Okay, just a second. Let me check. Just a second.
Okay.
Maybe my internet connection is slow. That's why I'm facing this problem. Just give me 2 minutes. I hope my screen is now visible.
It is trying to show something, but it's not fully visible.
Okay. Maybe because of the slow network, it will take hardly a few minutes, few seconds. Can you see my screen now?
Yes, the screen is visible.
Yeah, I'm.
Can you make it a full screen? Is it possible for you?
Yeah. Now?
Yes, please.
My sincere apologies for this delay. Myself, Dr. Poonam Jain from Department of Physics, Sri Aurobindo College, University of Delhi. And the title of my talk is The Applicability of VMI Model in Determination of Level Structure. The outline of my talk is the introduction, model, result, and the conclusion. In the introduction, I would like to give some brief idea about the lighter elements in which we have the ratio of n by z is 1. For the heavier element, this ratio varies and it will increase so that we have the unstable nuclei. So as we can see in the graph, the stable value is shown by the black line and the purple line which is showing the n by z ratio which is equal to 1. There are certain regions which are beta plus emitter, there are certain regions which are beta minus emitter, alpha emitter and spontaneous fission in the higher mass regions. So we can see the alpha decay takes place in mass greater than 209 and spontaneous fission decay takes place in the mass region 240. Now we have the deformed nuclei, the liquid rock model which and shell model. These both assume a spherically symmetric nucleus. This is a reasonable assumption for magic number nuclei. And if we have the quadrupole moment 0, then we have the spherical shape. And if we have the quadrupole moment greater or less, accordingly, we have the oblate or the prolate shape, respectively. Then later on came into the existence is the collective model, which is given by Bohr and Motteson, which has the axially symmetric potential, and that was the only model at that moment to give the explanation for the deformed nuclei. Now I come to the super deformed nuclei. The super deformation means a nucleus which is acquiring an elongated shape, which is represented by the longer to the shorter axis, which is almost twice. So from the shape, we can see for the spherical nucleus, these ratios are 1:1. For normal deformed nuclei, these ratios are 1.2:1, not double. And for the super deformed nuclei, these ratios are almost double. These are few mass regions for the super deformed nuclei which exist experimentally. So we can see in 190 mass region, in 240 mass region, means the mass region 1, 2, and 6, a major of the super deformed nuclei exists. In the lighter mass region also, the super deformed nuclei exist, but not in a very large number. The region 5 and 7 is very interesting because these are 150 to 160 mass region, and these are the rarer regions where the super deformed nuclei are found, and we are exploring them. Then is the energy level of super deformation. So this is a schematic diagram of the potential energy, which is a function of deformation for the fission isomer nucleus with a neutron number n. The liquid drop energy is modified by the shell effect to produce a double hump barrier with a second minimum for a super deformed shape. So here in the diagram, we can see the second hump, which is for the super deformed. For the normal deform, we have a single hump, and for the super deform, we have the double hump. Now the question came into the mind why theoretical studies in super deformation are required. As from the previous diagram, we can see over 350 SD bands in several different mass regions are reported till now. Unfortunately, the thing is the gamma ray energies are the only experimental information available to us. This is because of the non-observable discrete linking transition between the SD states and low-lying normal state. Nowadays, some of the nuclei are having a linkage between the normal deformed and the super deformed nuclei, but not all. So there is a major challenge for the theoretician as well as experimentalists to assign the spins, estimate the band head energy, and to calculate the excitation energy, which is related to the ground state for these particular nuclei, which is not at all an easy task. Also, these nuclei show multiple bands in experimental spectrum, so its direct study is very, very difficult. These are some of the general properties of the SD nuclei, where in this we can see a difference between the normal deformed band and the SD band. The normal deformed band, in which we can see on the right side, we have a perfect sequence of the energies, and on the left side, we have the spins 9, 10, 11, 12, and 13. While in the SD bands, we can see the energies are given in terms of 172.59 plus Y, something plus Y, something plus Y. Means these are not reasonably numbers which we have as an energy. And on the left side of the polonium band, we can see the spins are given as J plus 2, J plus 4, J plus 6. So again, this is a tentative value which the experimentalists cannot see it. So we are in the process of giving these estimation for the spins. Now the properties of SD nuclei. The gamma ray intensity decreases with increasing gamma ray energy. Some SD nuclei shows the rigid rotor behavior. SD bands have high excitation energy and high angular momentum. And over the last 3 to 4 transition, gamma ray intensity remains constant. Transition quadrupole moment vary with rotational frequency. This is another fascinating property of SD nuclei. They shows the signature partner pairs. Signature partner pairs means the band head moment of inertia and stiffness parameter for both the bands should be same. So this way, using the VMI model, we have predicted signature partner pairs as well, which is I have given here for the lead nuclei. Another is the odd even staggering. Odd even staggering in signature partner pairs means delta 1, delta I is equal to 1, means the transition energy sequence differ in 1 unit of angular momentum. And if it is delta I is equal to 2, then the unit of angular momentum has a difference of 2. So the another important property of the SD nuclei is the identical bands. Identical bands means those bands in which the different nuclei merely having the same energy and identical dynamic moment of inertia. So this example I have quoted here, in which we can see the transition energy in both the bands are 602, 646, 692, etc. And if we calculate the dynamical moment of inertia, that is also same. Now, in this particular work, I have focused on the triaxiality. Triaxiality, the nuclei which has large gamma deformation and large quadrupole deformation. These are known as triaxial super deformed nuclei. The important thing to note over here is that they have three principal axes, and these are different in length: shorter, longer, and intermediate axis. There is no symmetric axis, so K is not at all a good quantum number. If gamma is not equal to 0, then effective quadrupole deformation parameter may be defined by this expression. And for the TSD nuclei, the first one is invented for the lutetium isotope. So 163 lutetium was the first excited TSD band which was reported in the literature. This is the periodic table where we have the triaxial super deformed band. To orange color is showing that lutetium has several triaxial super deformed band, then thulium, then erbium, and so on. So I have using this VMI model, which is the theoretical model I have used here, which is a variable moment of inertia model. And with the help of this, I have tried my level best to find out the estimate the spins, band head energy, and the level structure of the triaxial super deformed band. This model was firstly proposed by Maris-Potti in 1969 to predict the ground state energy only in even nuclei. Later on, it was modified in 1990 to describe the rotational band in ordered rare earth nuclei with my supervisor and the group with small Coriolis coupling effect. SD nuclei, which are reported here, has composed of two terms. One is the potential energy term and another is the rotational energy term. VMI model is based on two parameters. One is the stiffness parameter and second is the band head moment of inertia. Band head moment of inertia and band head spin are the most important information which are required to study the SD band. Now, the formulation of VMI model. It is composed of the potential energy term which is given by Ji minus J naught whole square and rotational energy term which is h cross square upon 2J I times I plus 1. So finally, after taking all the calculation part, we are reached to the energy, which is the transition energy, and the band head energy for this is given as this expression. So this is the energy equation in which E naught gives the band head energy, and I is the moment of inertia, and J naught is the band head moment of inertia. Then energy value for I minus 2 is also given here. So transition energy, if I calculate for the super deformed band or the triaxial super deformed band, it will be EI minus 2. So the transition energy for the TSD band is given finally by this expression, which is in the elaborated form. And also we have observed the transition energy ratio, which is given by this expression. This is a lengthy expression, so I'm not going into the detail of this. Root mean square deviation method is just to verify whatever spin we have predicted is correct or not. The ratio of transition energy over spin is used in the super deformed band. Now, the focus on the work in the present study, our effort is to predict the band head spin of the triaxial super deformed bands by using the modified VMI model in rare earth region. Specifically, as from the previous diagram, it is shown that the maximum triaxial super deformed bands are found only in the rare earth region. The calculation have been performed for the 12 isotope in which the triaxial super deformed bands are available, which is thulium, lutetium, erbium, and hafnium, in which 44 TSD bands are available. We are able to predict the band head spin of the 20 TSD band in which the sufficient data for calculation is available. The main important point to note over here, why we are lacking in this data, because sufficient data from the experimentalist is not provided to us. So it is very difficult for the theoretician to go ahead without the sufficient data. Two parameters which we have calculated in this model is the band head moment of inertia and another one is the stiffness constant C. And with this we have fit using the best fit method, and using the RTOS plot we assign the spin for the TSD band to study the rigid rotor behavior. RMS deviation plots are compared with the RTOS plot just to confirm the spin for all the TSD bands. Now I am coming to my result part. So these are the 20 bands which I was talking out of.
Sorry for the interruption, ma'am. You have 2 more minutes.
Sure, ma'am. So out of that 20 bands, 16 bands I have shown here, in which we have a very good comparison between the gamma energies experimentally as well as VMI. And we are able to give the tentative experimental, we have the experimental data which is tentative, and we are able to predict the band head spin for the VMI model. So these are the graph for these particular bands, and in this graph, the lower is showing the value of the band head. So for example, 161 lutetium band 1 is having the band head spin starting from 15.5. If once we know the band head spin for any band which is not given experimentally, then we can have a complete level structure in terms of the spins as well as in terms of the energies. So this is the remarkable study which we have done in the triaxial super deformed band. And these are the RTOS plots which gives the rigidness. I think some of the workers want to know why SD band shows rigidness. SD bands has high angular momentum and they have very little decay time, so they are having the rigidness. And that rigidness is very clearly shown in this figure. As we see, there are lines which are going up, there are some lines which are going down, but there are a very few lines which are sticking to the straight. So this straight line is showing the SD behavior, the rigid rotor behavior of the band. Similarly, this diagram is more clearer and the other one is more clearer. So the conclusion, out of 20 SD band, 12 isotopes of thulium, lutetium, hafnium, we are predicted in the rare earth region. And we have the 16 bands in which the good agreement with the experimental value and 4 cases where we have the small disagreement by the 1 or 2 units. So we are able to calculate the spins for the hafnium where the tentative spin like J greater than 23, 24 are given. So we are able to find out that as well. And we have got the reasonably good fit for the transition energy and the spin which is suggested by the model. Thank you so much for the attention. And now I would be happy to answer the question if any.
Thank you, Dr. Jain, for this nice presentation and the results. We have one question from the audience. Why SD nuclei show rigid rotor behavior? But I think you have already explained this. But if you want, you can explain a bit more.
Yeah,
in 1 or 2 sentences.
I have already given the reason to why SD bands have rigid rotor behavior. The reason is, again, I am mentioning the SD bands has high angular momentum and they have very low decay time. Because of that, we are not able to find them experimentally so well. But still, experimentalists have very good detector and they are having the very good data. But still, we are lacking somewhere because there is no linkage between the normal deformed band and the super deformed band. So this SD bands are showing rigid rotor behavior. This we have seen experimentally as well as theoretically by the graphs. The straight line is showing the rigid rotor behavior.
So, thank you so much. Is there any other question from the audience?
Dr. Bhattacharya, can I ask a question?
Please, ma'am. Please go ahead.
I just want to know why some nuclei are behaving as a super deformed. Is there any interaction that causes this deformation?
Yes, ma'am. Very nice question. Actually, ma'am, see, we always expect the nuclei are spherical in shape. Whenever there is a rotation in the nucleus, whenever there is any deformation which is there inside the nucleus, then they change its shape, which we call is at a deformation. So till now, we know the nuclei have normal deformation, which is in terms of the prolate and oblate nuclei. But the moment we explore more and more region, then we came across the super deformed band, in which this deformation is the level, the minor to the major axis is approximately double to each other. In that case, the shape is, as I shown in the first slide, the shape is very much different from the spherical, this slide. I hope you can see. So this deformation is very high, and this is very difficult to study this deformation. Reason one, we are not having so precise accelerators right now in India as well as abroad to detect these nuclei, particularly in the higher mass region like actinide region. And second problem with the theoreticians is these bands are not having any linkage with the normal deformed band. Once we have the linkage with the normal deformed band, it is very difficult for us to have the information about the energy as well as spin. But since there is no linkage in the data sheet, so we are not able to get from where these bands are basically starting. So that's why these bands need more attention, and these are so particular to be explored.
Yes, okay. So it is left for research till now, okay?
Yes, ma'am. This area is totally open for the research.
Yeah. Thank you.
Thank you, ma'am.
Is there any other question? Okay, if not, then let's thank the speaker once again. Thank you, Dr. Jain, for this wonderful presentation.
Thank you, ma'am.
I can see that Dr. Yogesh Kumar is here. Dr.
Yeah, I am
Dr.
here.
Yes.
Am I audible?
Yes, you are perfectly audible.
Yeah,
So,
I'm sorry
can you
because
please...
my laptop is completely asking for update, so I have
Oh.
connected with the mobile phone only.
Okay. No problem. So,
Yeah,
can you please share your screen?
yeah, I just try to share my screen. Yeah, can you see my screen?
Not yet.
Yeah, is it visible now?
Yes, now it is visible. Can you please make it full screen? Is it possible?
Yeah. No, ma'am. I don't have any idea.
Okay, fine. So
Yeah.
please go ahead.
So sorry for the inconvenience. I thanks the organizer for giving me the invitation to deliver a talk on expansion of QGP droplets in presence of magnetic field. I am Yogesh Kumar from the Department of Physics, Hansraj College, University of Delhi. So I will talk about the expansion of QGP droplet, where my outline, I just cover some overview of the quark-gluon plasma, then some motivation part and work regarding this statistical model. Then I will show my some of fascinating results, and finally I will summarize my work. So these are two outstanding property of QCD. One is taken as asymptotic freedom, which exists at a very high energy and small distance scale, where quark and gluon behave like a free particle. On the other hand, we have the confinement where quark and gluons are just confined within the hadrons. And here, non-perturbative QCD is the useful tool. The ongoing experiment at RIC and LSC provide us the best opportunity in various regions of temperature and chemical potential. And at some critical temperature around 170 MeV, the hadronic matter is supposed to undergo a phase transition into a new phase that is called as quark-gluon plasma, where quark and gluons behave like a free particle. The study has attracted great interest in various regions of temperature, like we can study the QGP just after Big Bang, where the temperature is about 170 MeV, and also in the core of neutron star, where the density is 5 to 10 times of the normal nuclear density. We can also study the QGP at least lattice QCD simulation, and also in heavy ion collision like relativistic heavy ion collider situated at Brookhaven National Laboratory and Large Hadron Collider at CERN. Now we have the motivation and work part. Like other QCD treatment, it is almost impossible to deal with the QGP because of the complexity of the system. Because whenever we try to investigate the phase transition between hadronic matter and QGP, it's the idea to represent the phase boundary of between the QGP droplet and bulk hadronic matter makes one bit uneasy in the MIT bag model. Also, it was pointed out that by the Peshier, there is a disagreement with the numerical experimental result, which is shown as for the pressure and bag constant. So we use the statistical model for the analysis of QGP fireball formation, and we also can produce the equation of state of QGP. So the model has it in its merits, in its simplicity and robustness to give qualitative and quantitative idea about the quark-gluon plasma. So using basically our Ramanathan, where our model is restricted to the Ramanathan bag model, and we have just modified the Thomas and Fermi model, which is used for the atom, and Bethe model for the nucleons. So as you can see here, Thomas and Fermi have developed the density of state for the electron. In the same way, on the same footing, we have modified the density of state for the quark and gluons, which is given by this expression, this integral part. And similarly, we can modify this integral into the differential part as well, where this small v represent at the volume of the QGP droplet, and v is effective is the effective potential. And that effective potential we can obtain by the thermal Hamiltonian. And this K is the 4 momentum transfer. Using this, we have modified the density of state for the quark and gluons. And of course, this effective potential is nothing but the use of the thermal Hamiltonian for the quark and gluons. We can see that in this effective potential, we have used this gamma, Q, and G value. And G is the QCD running coupling constant, where T is the temperature. This phenomenological parameter we used as gamma Q as 1/6 and gamma G as 6 times of gamma Q, or 8 times of gamma Q. This value basically we use as a phenomenological hydrodynamical model, and this values are nicely fit into our calculation to give the finite result and also avoid the infrared divergences in our calculations. On the other hand, this K minimum is the minimum cutoff momentum, which gives the result finite result, hence avoiding the any infrared divergences. So here the gamma value is taken as the inverse root mean square value of flow parameter for the quark and gluons, and it's just like a Reynolds number, which gives the nature of the QGP flow. On the other hand, we have the Weil density of state given by this expression, where capital R is the radius of the QGP droplet. And the basic idea here is to treat with the QGP, which composed of 3 flavor of quark. We can use 2 flavor, 2+1, or 3 flavor of quarks, which is confined within the volume V. And outside the volume V, we have the pions. And using this, our aim is to calculate the free energy for whole the system, which can be used to calculate the various thermodynamical variables. So using this density of state, now we compute the total free energy, by which we first try to compute the free energy for non-interacting fermion and boson, which is given by this expression. So this minus sign indicate for the fermion and plus sign for the bosons. G is the Gi is the degeneracy for the quark and gluons, and rho I is the density of state for the quark and gluons. We also replace this dynamical quark mass as the finite quark mass, which is represented by this Mi symbol. And Mi is here the mass of the up, down, and strange quark. On the other hand, we have the another important term taken as the free energy interface term given by this expression. So this interface free energy term separated out the hadrons from the QGP term. The third important term, we have the free energy for the pion given by this expression. This is the standard relation we have used in our calculation part. So ultimately, by the use of free energy for the quark and gluons, then free energy for the interface term and free energy for the pion term. By clubbing all these terms, we try to find out the total free energy of a given system. And this total free energy is very much useful to create the finite QGP droplet in the pionic medium. And with the help of this total free energy, we can also calculate other thermodynamic parameter like pressure, energy density, entropy, specific heat, speed of sound, etc. Now coming to the result part, now you can see here that we have plotted the free energy. We have calculated draw the free energy versus radius of QGP droplet with the by fixing the physiological parameter as gamma q is equal 1/6 and gamma g is 10 times of gamma q. And for the pion term, for the surface term, you can see we cannot able to find out the stable QGP droplet formation. My right hand picture, you can see that by varying different temperatures, my free energy continuously increases by varying the temperature and with the radius of QGP droplet by using these phenomenological parameters. So we are not able to find out any QGP droplet formation with these phenomenological parameters. But on the other hand, whenever we fix gamma q as 1/6 and gamma g as 6 times of gamma q, the total free energy, whenever we plot this total free energy versus radius of QGP droplet by varying this temperature from 150 to 250, we found that the free energy first goes on increases and then it goes down. So the barrier height, we have seen that for the positive height barrier and then negative height barrier. So this will give me the physical picture of the QGP droplet. So by that, so by this, we can able to calculate the total free energy of a QGP droplet formation. So using this in another picture, whenever we see the intercept of this, it will give me the real physical picture of the QGP droplet formation. Then we have plotted the entropy versus temperature curve, where we found that at some transient temperature about 160, there is a weak first order phase transition predicted by our model. Then we have modified our model as the effective quark mass, which replaced the thermal quark mass by coupling all these three mass term. Like first is the current quark mass, then coupling of the quark mass and thermal quark mass, and third is the thermal quark mass term. So in this part, we have modified the energy term as well, where we have used this because this heavy ion collision can create the a huge magnetic field, which is of the order of 10 to the power 15 Tesla at RIC and 10 to the power 17 Tesla at Sun. Using that, what we have found in our result that whenever we use this magnetic field around 0.2 GeV square, we found a huge QGP droplet formation. As you can see, if I compare my graph from the previous graph, then by putting this, by considering this magnetic field, my evolution for this free energy quark will give me the very large QGP droplet formation. So the bunching of this curve at the some part, it give the more realistic picture for the stability of the QGP droplet. We have played with the
Dr. Kumar, you have 2 more minutes.
Yeah, ma'am. I'm just finishing out. So we have played with the other thermodynamic parameters that we have used the chemical potential, like we have put 50 MeV chemical potential by putting my fixing my magnetic field 0, and we can see that whenever we use this chemical potential or considering this chemical potential, our system is highly affected, and this QGP droplet goes on decreasing whenever we increase the chemical potential value. So at very low value of chemical potential and at finite magnetic field, we found a large QGP droplet formation. We have also produced the equation of state, like we have produced the pressure, energy density, entropy, and speed of sound. In all result, our results, theoretical results match very well with the lattice QCD result. And by increasing this magnetic field, our results are also enhanced. So finally, I conclude my results that the model we have discussed here is not only simple, but that's a lot of physics about the formation and evolution of the quark-gluon plasma. So overall, our results are folded with a model which explain the evolution through the thermodynamic variables like free energy, entropy, another thermodynamic parameter, and it also helps to produce the equation of the states of QGP. So finally, our statistical model give very fruitful result, which must be very useful at RIC analysis. Thank you very much. If you have any question, then I'm happy to ask.
Thank you, Dr. Kumar. Thank you for this nice presentation. Is there any question?
Can I ask a question, Dr. Bhattacharya?
Yes, ma'am, please.
Yes. Thank you, Kumar, for your nice talk, and it's nice to see you see you again in this YMP.
And I'm very sorry because here the network problem is there and my laptop is also hanging out.
It's okay. Finally, we have the session. I just want to know in your, I mean, what there is a very wide range of droplet size. So can you say anything what actually experiment says about the maximum droplet size?
Yeah, actually the maximum range of droplet size we generally consider about 6 to 8 Fermi. But
it is large. I mean, you have seen a very large 8 Fermis or something like that.
Yeah, in our case, it is about 8 to 10 Fermi around.
I think he lost his connection actually.
Okay, thank you. Thank you for the answer.
Let's wait for another minute if we can join.
Hello.
Yes, now you are audible. Yes, now you are audible.
Yeah. Yeah, what I'm saying that our model prediction have the sufficient range of the this droplet size, where we have taken the droplet size from let us say 2 Fermi to 12 Fermi around, and this intercept will give some range of the QGP droplet, which give rough value around 8 Fermi to 10 Fermi around. But yes, because RIC and LST result have not yet confirmed what is the actual size of this QGP droplet, so it is difficult to predict that QGP droplet size.
They are predicting much more smaller than that, I think so. That's what I
yes.
literature, yes. So your work is very interesting, particularly the effect of magnetic field on the droplet side is something new. Yeah, this is very nice. Thank you so much.
Thank you, ma'am. Is there any other question? If not, then let's thank the speaker. Thank you, Dr. Kumar, for the nice presentation and for the wonderful discussion. Let's move on with the next talk by Dr. Mili Das from Anandamohan College, Kolkata, and she will talk about the physics as a sleuth. So, Dr. Das, are you there? Dr. Das, are you there? I can see your screen, but you are not audible.
Am I audible, ma'am?
Yes, now you are audible. Please continue. Dr. Das?
Yes. Am I audible?
Okay. Yes, you are audible. Please start.
Okay. So with sincere thanks to the organizer of YPM 2023 of Adams University, I am starting my presentation. Its title of my talk is Physics as a Sleuth. And I'm teaching physics in Anandamohan College. So the motivation of my presentation is, these days in medical diagnostics, the imaging of internal body parts is indispensable. And here, physics plays a crucial role in the instrumentation and techniques that produce these images. Now, depending on the organs and the suspected ailment, physicians prescribe some sort of imaging techniques. That is, in some techniques, we use ionizing radiation. Sometimes we use radioactive nuclei, sometimes large magnetic field, and in other cases, sound waves. You can just correlate that ionizing radiation is used in X-ray, radioactive nuclei is used in PET, and large magnetic field is used in MRI, and sound waves, they are used in ultrasonography, medical ultrasonography. Now, the next thing is the primitive one, that technology, imaging technique, that is X-ray. X-rays are electromagnetic radiation with wavelengths between 0.01 to 10 nanometer. And it was discovered by German physicist Wilhelm Conrad Röntgen. And we know that in 1895, he discovered this, and he won the first Nobel Prize in physics in the year 1901. But he didn't accept this Nobel Prize money, and we know that later he died of poverty. Now, the production of X-rays, basically Röntgen noticed the first X-rays emitted from the anode of Crookes tube, a type of discharge tube. This is the Crookes tube, where a cathode is there and anode is there, some accelerating potential is there, and water in, water out for cooling purpose. And here, X-rays are produced when the energetic electrons hit the metallic anode, that is here. Okay. The more modern water-cooled Coolidge tube was invented in 1913, and a similar design is still in use. And at that time, it was unknown to Röntgen, so he coined the term. Unknown means some in algebra, that is X, so it is X-rays. And these rays are basically used for detecting bone fractures, tumors, pneumonia, calcifications, foreign objects, or dental problems. And in research, we can use in crystallography, nuclear detector development, airport security. All of you know that in baggage scan, we use basically X-ray, and medical use, of course, I have mentioned. Now, the next slide. It is the computed tomography or CT scan. And CT scan is nothing but the 3D X-ray thing. It is basically they use the technique of X-ray and combined with the computer processing to generate a series of cross-sectional images, that is the 3D images. Here, this is the patient table, and this is called gantry. Here, the gantry 3D image, this ring is rotating, and this is T is basically the T is basically the X-ray tube, and D is the detector. And before coming to the proper CT scan, I want to mention the technique of X-ray, how come we are getting the images, that is X-ray absorption basically follows Lambert-Beard law, that is intensity I equal to I0 into e to the power minus mu L, where I0 is the incident intensity and mu is the sample's linear attenuation coefficient, and small l is basically the path length that X-ray traverses. Now we can correlate our knowledge that X-ray basically our bone is made up of this bone very quickly absorbs X-ray, and it is made up of high Z element, that is calcium Z equal to 20, because this absorption actually is proportional to this Z value, atomic number, and mass density. So bone is made up of Z equal to 20, so it absorbs X-ray very quickly, and light cannot pass through the bones, and so it appears whiter on the radiograph, and X-ray passes very quickly to tissues, muscle, fat, and air cavity filled lung, so we can get those things gray on the radiograph. This is the technology. And the CT scan, rather a 3D image, though the ionizing radiation X-ray use and the same ionizing radiation in larger dose used in CT scan. So CT scan is not very healthy not very healthy because of these radiation doses, but clear picture 3D image it is giving, and it is used to detect neurological disorders like Parkinson's, Alzheimer's, etc., heart disease, pneumonia, chest condition. And here the picture basically left thing is showing collection of blood in brain, and right thing tumors in both sides of brain. This clear image, and this technology actually invented by Alan MacLeod Cormack and Godfrey Hounsfield in 70s. Now the next thing is basically positron emission tomography, PET, in abbreviated form. So PET is a technique where enhanced metabolic activities is located using positron emitting radionuclide. What type of radionuclide we use? That short half-life radioactive tracer, that is like 18 fluorine, half-life is roughly 2 hours and is incorporated into a biologically active molecule most commonly used fluorodeoxyglucose, that is called FDG. So this agent is then injected into the living subject, means in our body. And waiting time is, if the FDG is the molecule using, so waiting time is 1 hour, and during which the active molecules are concentrated in the tissues with enhanced metabolic activities. And after a waiting period, the patient is taken to the scanning room. Now, this source here is the source. This is not my slide. I have taken it from here. So this is the 18-fluorine nucleus. So this 18-fluorine is radioisotope, and it emits E+, that is positron. Paul Dirac said for the first time about this. And this positron actually will lose energy within the tissue, and it will find within 1 mm, it will find some electron and both of these positron and electron will annihilate to produce 2 photons. Each photon is having the energy 511 kilo electron volt, and these photons are detected by the scintillator detectors, and scintillator detectors are placed like here. The scintillator detectors are placed at the ends of the gantry ring, at two ends of the gantry ring, which actually this is the chord of a circle. This is the chord. Okay. Actually, this here and here 2 scintillators are produced, because these photons are coming back-to-back photons, they are called, because they are 180-degree apart. And if we can detect it with the help of scintillator detectors in coincidence, that means within short time interval, if these 2 photons are detected, then this E+ and E- will annihilate to give these 2 photons. Then we can just say that this chord is joined then, and many of these chords, intersection point of many chords will give you the location of your malignancy. Malignant tumor, to detect this PET scan is used. Now, the procedure in language, we can say that this active molecules start emitting positron, and whatever we have mentioned this, that within 1 mm, it decelerates to a point, and then back-to-back photon. Okay, everything we have just covered. Okay. So it is a very important positron emission technique. Only thing is here we need actually cyclotron, because cyclotron will produce that radioactive nuclei where proton is bombarded with some target, and then that radioactive nuclei will emit that positron. So for this PET study, we need basically cyclotron, or we need some half-life more than 2 hours to carry the things. Now, the next thing is, this is the source. I have taken the images of PET, that the normal brain is showing like this, and a brain tumor demonstrated on the right, blue indicating poor blood flow at the area of tissue damage or tissue death. And in the brain cell, if the tissue is damaging or the death of tissue is showing these cause the disease, dementia, Alzheimer's, etc., loss of mental functions. Now we use another technique, like in CT, X-ray, and PET. We used basically ionizing radiation, and doses will be compared in the later slide. And ultrasonography, the technique we use is very different. We use basically sound wave, but the sound wave we use is beyond our audible upper audible limit, that is human hearing 20 kilohertz. More of often we use 1 to 18 megahertz frequency. Now this sound wave actually propagates, and the reflection from the reflection of sound wave, we actually get the information about the oxalate or calculus in kidney, etc., etc. Now, the medical ultrasonography, Austrian neurologist Carl Theodosic with his brother Friedrich, a physicist, made the first ultrasonic echo image of ventricles of a human brain in 1941. This technology, or this technique, ultrasonography, is used in detection of flaw in solid material, and to measure navigate or to know the depth of water, measure the depth of water, we can also use this. Now, how to produce this sound
Dr.
wave?
Das, sorry for the
Yes,
interruption. You have just 2 minutes left.
Okay, okay. So how to produce, because the sound wave of frequency is produced by a piezoelectric transducer. Piezoelectricity means this piezoelectricity is something which is mechanical stress through electrical pulse generator, and that then it converts to sound wave, and the sound wave is reflecting from the source where our primary interest is, like we can monitor through USG the fetus, the growth of fetus and some gallbladder, kidney stone, etc. And these sound waves, we have to measure the strength of echo and measure the time to receive the echo. From that, we can just get the idea of these things. Now, the last thing is MRI or magnetic resonance imaging. Here, a medical imaging technique. At first, the name was nuclear magnetic resonance (NMR). They are the recipients of Nobel Prize in Physics 1952, and later 2003 Nobel Prize in Medicine. Peter Mansfield and Paul Lauterbach, they got the Nobel Prize for MRI. Nuclear term actually creates some phobia, so later we removed this term, and MRI is the common name. So this medical imaging is done. Human body is largely composed of water molecules. Water molecules means hydrogen nuclei, and this hydrogen nuclei means protons, means UUD structure, and means one unbalanced spin would be there, and intrinsic magnetic moment would be there. And due to this intrinsic magnetic moment, if we just apply some strong magnetic field like this, then it will start to align themselves. In our body, the hydrogen nuclei are there. And then if we apply a small perturbing electric field RF along this direction, then a change, like this slide shows, this change in response to the force, if we apply some electrical pulse RF, then in response to that pulse force bringing them back to their equilibrium orientation, the protons undergo a rotating motion, and these changes in magnetization alignment cause changing magnetic flux, which yields changing voltage in receiver coils, producing the signal. MRI is, the caution is the magnetic field is so high that is 0.5 Tesla to 1.5 Tesla. In abroad, this is 3 to 7 Tesla. It is so high that it can pull a car. So very careful, we should be very careful about this, because in recent days in Woodlands Hospital in Kolkata, we have seen that some oxygen cylinder, it pulled an oxygen cylinder which hits basically a technician. An advantage is no ionizing radiation here we use, but disadvantage is a patient is having pacemaker, or after some orthopedic surgery, if he has some steel plates, he is unable to cannot undergo MRI. So MRI is used to detect a very, very clear image of ligament injury, and in the brain, MRI can differentiate between white matter and gray matter. And next, the comparative study, procedure X-ray arm or leg. Just see the average effective dose we receive. If one X-ray is done, 0.001 millisievert, X-ray chest 0.1 millisievert, like CT chest 7 millisievert, and CT angiogram 16. But don't worry, because if we eat one banana, it contains 40 potassium, which actually we receive 0.1 microsievert of radiation. And here is this comparative study between CT scan and MRI. CT scan, PET CT everywhere, X-rays are used, large magnetic field is used in case of MRI, and spatial resolution is very high in case of MRI, and exposure to ionizing radiation here in CT scan is there, which is actually harmful. MRI has no side effect, or it is not that harmful because it does not use any ionizing radiation. And in contrast, here we use some medium which causes kidney problems, etc. But here a more safer contrast is used, that is gadolinium. And if we compare the CT brain, which costs ₹1500, and MRI is a little bit costly, because for the same thing, for brain MRI, it costs ₹5,000. So my summary is actually the widely used diagnostic imaging techniques that are prescribed by the physicians. They derive their working principle from physics or the technique actually revolve around the fundamental laws of physics. So thank you.
Thank you, Dr. Das, for this general overview of the different medical techniques and the physics behind it. Thank you for this nice presentation. I really believe that this will help our students to get an idea about these techniques and the equipment. Is there any question from the students and from the audience? I think no. So let's thank the speaker once again. Thank you, Dr. Das. And let's move to the next presentation by Dr. Tushar Kanti Bose from Sri Krishna College. And he will talk about the generalized quantum coins and the dynamics of disordered quantum walk. Dr. Bose, are you there?
Yes. Am I audible?
Yes, you are audible. And your screen is also visible, so you can start.
Okay, thank you. Hello and good afternoon, everyone. I am Tushar from Sri Krishna College, West Bengal. First of all, I would like to thank the organizers for giving me this opportunity to present my work in front of you. Today, I will be discussing some of my ongoing work on the dynamics of phase disordered quantum walk. So this is my plan of talk. Firstly, I will briefly describe about quantum random walks and different types of disorder in quantum random walks, and then I will present some results of our study. We have studied joint effect of generalized coins and phase disorder on quantum walk and individual effects of phase aperiodicity and single point dynamic phase defect on quantum walk. So what is classical random walks? I think all of us know about classical random walks, that a classical random walker has a classical coin which has two sides, head and tail, and he tosses his he or she can toss his or her coin. If it is head, say he or she can jump one step towards his or her right side, and if the result is a tail, then he or she can jump one step left, one step towards his or her left side. In this way, the walker can successively toss the coin and trace a path along the one-dimensional axis. Since the coin tossing is a random event, in this way, the walker can trace many different paths. And if we take an average on all different paths, the overall average probability distribution looks like this red dashed line on the on this figure. This Gaussian distribution is generated from the classical random walk. So after a long time, it is highly probable that the walker returns to the origin. On the other hand, this black continuous line shows the probability distribution of a quantum random walk. So these two distributions are completely different. So what is different in case of quantum random walk? In case of quantum random walk, the walker has an internal degree of freedom which is called spin or chirality. And in case of quantum random walk, all different classical paths can interfere quantum mechanically. So in case of quantum walk, there are two different unitary operators. One is a rotation operator, which is called quantum coin, and the other is a shift operator. So the quantum coin acts on the walker's internal degree of freedom. So the walker can be in a superposition state of spin up and spin down. And then the shift operator shifts the walker according to the internal state. If the walker is in a spin up state, the shift operator shifts the walker, say, on the right side, one step towards its right side. And if the walker is in a spin down state, the worker shifts the worker on the opposite side single step. In this way, successive application of the quantum coin and shift operator generate discrete time evolution of the worker. And so this black continuous curve is the result of the probability distribution of the quantum work obtained with a symmetric coin and a symmetric initial condition. So in this case, the worker after a long time, the worker can. It is highly probable that after a long time, the worker can be found at a position which is quite distant from the origin. So this is one major advantage of quantum work in different type of applications, that the quantum worker spreads in a much faster way than the classical random walk. So the major advantage is that the standard deviation in this case grows linearly with time in case of quantum random walk, and in case of classical random walk we get diffusive behavior. So another interesting feature is the quantum entanglement between the internal and external degree of freedom. Quantum entanglement is a feature which is highly attractive from the point of view of quantum information and quantum communication. In this slide, I'm showing one popular coin operator, which is called the Hadamard operator in equation number 1, and a popular shift operator. So the structure of shift operator looks like this, and we have considered this initial state in all of our work, that the quantum worker, there is 50% probability that it is in spin up state and 50% probability that it is in spin down state. We have measured two different observables. So there are several different observables in case of quantum random walk, but we have focused on two particular observables. One is standard deviation and other is entanglement entropy. This is the common standard deviation formula, and the standard deviation in case of quantum random walk it depends on time, can depend on time in different ways. So we have considered that the standard deviation sigma goes as t to the power alpha. This alpha is an exponent which can vary from 0 to 1. If it is 1, then it is the ballistic behavior. If it is 0.1, then it is diffusive behavior. And if it is in the range 0.1 or 0.2, then we say that there is the localization. And the entanglement entropy is measured by the conventional von Neumann entropy using the reduced density matrix. So this is the formula of entanglement entropy, and the lambda is the eigenvalues of the reduced density matrix. So entanglement entropy has becomes 1 for maximally entangled states, and it can be 0. It is 0 for separable states, and intermediate values of entanglement shows intermediate values of this entropy. Okay, now let us discuss different types of disorder. There are, in general, two different types of disorder. One is dynamic, that is time dependent. The other is static or time independent. Both dynamic and static disorder can be generated in different ways. Say, for example, one can use different coins at different positions or time to generate coin disorder. So this is the structure of a generalized coin in equation number 3. So this is the coin depends on 3 different parameters: rho, theta, and phi. So rho can vary from 0 to 1, theta can vary from 0 to 2 pi, and phi can also vary from 0 to 2 pi. In case of dynamic disorder, these parameters become dependent on time. In case of static disorder, these parameters become dependent on position only. There is another type of disorder which is called phase disorder. In this case, the coin remains fixed, but the worker picks up some random phase e to the power delta when it hops into certain sides of the lattice, and in this phase can be random. It can depend on time or on position. So when it depends on time, we get dynamic phase disorder. When this phase depends on position only, we get static phase disorder. So let me show you some results on phase dynamic and static phase disorder. These results were published by Jane and Young in 2017. So they studied both static and dynamic disorder. They generated static disorder using an array of random but time independent on-site phases. And they generated dynamic disorder using the disorder they generated dynamic disorder when the array of random phases was updated at each step. So the top two figures presents the variation of sigma, the standard deviation, against time. The figure on the left hand side shows the variation of sigma in case of static disorder. We can see that for some particular values of delta, the phase parameter, there is localization. That is sigma, the value of sigma does not grow with time. So static disorder, static phase disorder generates localization. Whereas on the right hand side, this figure does not show any localization effect. Although in both cases, the value of sigma decreases with increasing value of delta. And for in case of entanglement, the two figures on the bottom shows the variation of entanglement with time. In case of static disorder, the entanglement reaches a high value, but not the maximum possible value, which is 1. But in case of dynamic disorder, the worker generates maximal entanglement for certain values of delta, certain non-zero values of delta. For smaller values of delta like 0.1, 0.3, there is maximal entanglement. So now we have these results were generated using a Hadamard coin. Now we have introduced a generalized coin. So this was the structure of generalized coin in equation number 3. We have used generalized coin and studied what happens when we vary the parameters rho, theta, and phi. So now these are the results. So these two figures, green colored figures on the top, these are actually contour diagrams. Here, the value of sigma has been plotted as a function of theta and phi, and this is the color bar. So if the value of sigma is high, then there will be red color, and if the value of sigma is low, it will be dark blue color, and the intermediate colors indicate intermediate values. But here there is only one color throughout the figure. It indicates that the sigma remains practically independent of theta and phi. This figure has been generated for a particular value of rho, that is 0.20. We have also studied a higher value of rho, studied the evolution for a higher value of rho, but the results remain the same. So in case of dynamic phase disorder, the value of sigma is quite independent of the coin parameters. On the other hand, entropy becomes dependent on sigma. But again, these are the contour diagrams. This is for the first.
Excuse me, sir. Sorry
Yes.
for the interruption. So, if you kindly complete within few minutes, it will be fine for us.
Okay. Okay. I will take 2 more minutes. So these two figures are for dynamic disorder, and these figures show that the entanglement entropy increases with the increasing value of rho. So in case of dynamic disorder, entropy depends on rho. The final figure in this slide, you can see that there are different stripes. So different stripes are for different values of theta. So entanglement entropy in case of static disorder depends on theta. So we have also studied the static phase aperiodicity. In this case, the difference between a random phase disorder and static phase aperiodicity is that the phases are changed according to a binary sequence. We have considered the popular binary Fibonacci sequence. The findings are the following: that the binary Fibonacci sequence, it gives us faster spreading and absence of localization and higher entanglement entropy in comparison to the random disorder case. And we have also studied single point dynamic phase defect. The most interesting result is that in case of single point dynamic phase defect at origin, one can achieve maximal entanglement in case of deterministic disorder. So it is quite interesting in respect of quantum communication and information that there is a way to generate high value of standard deviation, that is sigma, which is sigma is proportional to time, linearly proportional to time in this case, and also high value of the maximum value of quantum entanglement in a particular setting. So it is quite rare. So let me summarize the results. We have studied 3 different aspects of quantum walk. We have studied the influence of coin parameters on phase disordered quantum walk. We have found that the entanglement entropy mainly depends on the coin parameters rho and theta, not phi. It depends on rho and theta respectively in cases of dynamic disorder and static disorder respectively. However, the standard deviation remains nearly unchanged as a function of coin parameters for both types of disorder. We have also studied static phase aperiodicity in quantum walk. We have shown that it results faster spreading in comparison to the static random disorder case. In contrast to the static random disorder case, there is no localization phenomena. It also offers higher entanglement entropy in comparison to the random disorder case. Finally, we have also studied influence of single point phase defect. Here, entanglement increases with the phase parameter delta. Single point deterministic dynamic phase aperiodicity at x equal to 0 produces maximal entanglement. This is the interesting point. Okay, thank you for your kind attention.
Thank you so much. So anybody, if you have any questions, participants, please write in chat box, or you may ask the speaker directly. Any questions? No questions. So thank you so much. Thank you so much, Dr. Tushakanti Bose. Thank you so much. It was really informative talk. Thank you so much for joining us. So now I would like to request Mr. Piyush Pallab. He's the project assistant of Adamas University.
Am I audible?
Piyush, are you here? Yes, you are audible. Please share your screen. He will be talking on spectroscopic analysis of 197 Mercury nucleus. Please share your screen and start your presentation.
Okay. Is my slide visible? Okay.
Okay, fine.
So it was 1911, and somebody put an alpha source in front of gold foil and surrounded by fluorescent sheet, and he discovered a nucleus. That was Rutherford. And since then, we all are curious about the structure and functioning of the nucleus. So, good evening, ladies and gentlemen. I am Piyush Pallab, Project Associate 1, Department of Physics, Adamas University. So, and today I will be talking about spectroscopic analysis of 197 Mercury nucleus. So, why I quoted about Rutherford's work in the beginning? We do the same thing, but in a more advanced manner. Just like in Rutherford's experiment, the weak alpha source is now replaced by a very powerful cyclotron, the particle accelerator, and the target is now are much thinner and purified targets. And in place of fluorescent screens, we have highly sophisticated detectors. So here's the plan. We need to study 197 Mercury nucleus, whose half-life is 64.14 hours, and this is a non-natural occurring isotope of mercury. So we need to populate this isotope in the laboratory in order to study this. So how do we do it? So I am keeping this slide very simple and in a very vague manner. So if we take platinum target and bombard it with alpha, it will give us the excited state of mercury, and eventually we will get 197 mercury. So this entire process is known as fusion evaporation reaction, in which the target nucleus got bombarded with a projectile nucleus. Then both of them got fused and they become a compound hot system. Then this hot system starts releasing energy in the form of particles and goes down, becomes cool, and at some point it is still hot, but don't have enough energy to release any further particle. Then it undergoes gamma emission, and that's where we start our calculation, because these gamma transitions coming out from those compound nucleus carry the signature structure of the nucleus. So here is the entire plan simplified on paper. We have a cyclotron, we have a target, and we will bombard alpha particles on the target at with the energy of 52 mega electron volts. Then the target will give us gamma. We will detect those gamma with our high purity germanium detectors. Then we will acquire those signals from the detector using multi-channel analyzer, and we will save it to our digital acquisition system. We also need to bias our detector in order to get it functioning. So let us talk about the target. Our target was 97% enriched 13.6 milligram per centimeter square thick 198 platinum target, which was set on an aluminium holder, self-sustaining target. Talking about detectors, we had 8 Compton suppressed Clover high purity germanium detectors, 2 at 125 degrees, 1 at 40 degrees, 5 at 90 degrees. Also 2 low energy positron spectrometer, 1 at 40 degree and another at 125 degrees. So why we need to put these detectors at different angles, and how we do that? So we put these detectors at different angles for a very specific purpose in order to calculate DCO and polarization asymmetry, which I will talk in next slides. So how do we put that? So we use this, a frame. We set our detectors at different angles in these frames, which is made out of stainless steel, a very robust structure this is. And after connecting every wires and giving the bias to the detectors, this is how it looks like. This is Indian National Gamma Array at Variable Energy Cyclotron Center, Kolkata, which is a very robust system designed and functioning for nuclear structures and gamma ray spectroscopy. So when our system is hot and functioning, then we started acquiring data. So after that, we need to process huge set of data. So first of all, at the first step, we dump and sort our data using PickShot, which is the software package developed by UECDA CSR Center, Kolkata, and through which we get gamma-gamma coincidence matrix, gamma-gamma coincidence cubes, and other symmetric and asymmetric matrices for DCO and polarization calculations. For the visualization of spectrum, we use Radware package. Okay, this is a gated spectrum, which is this is the end product after analyzing and visualizing all the data. Here you can see that all the blue gamma energies are from 197 mercury, but there are a few red gamma also, which are from contamination, which was 198 mercury, which was also populated during the reactions. All the star mass gamma energies, gamma transitions shown here are newly discovered gamma energy, which has not been seen ever in previous experiments. Using these gamma energy coincidence matrices, we set up place our gamma transitions into correct places. After correct placement of the gamma, we need to assign spin and parity of the levels. So for spin and parity of the levels, we need to determine the DCO ratios and polarization asymmetry ratios for that. So before calculating DCO ratios and polarization and eventually calculating the spin and parities of unknown levels, we first tested our data on known and previously quoted data from previous literatures, and it was well in agreement. So from this confidence, we assigned the spin and parieties of the unknown transitions which were discovered in our experiment. After doing everything, setting up the placement of gamma and assigning spin and parieties, this is the partial de-excitation scheme of 197 Mercury. Here you can see all the star marks gamma are newly discovered by during our experiment, and you can see we have discovered band B4 and B5, and band B4 we have calculated and analyzed as identified as a rotational band. In the negative priority side, in the positive priority side, we also have many new gamma transitions. The band B1, B11, B10, we have discovered these gamma transitions. So in conclusion, after a successful experiment and data analysis, we have established the de-excitation scheme of 197 Mercury. At a total of 19 new transitions were found. We have assigned spin of the levels by calculating DSO ratios. We have done successful measurement of polarization asymmetry values for many new transitions and assigned parieties of the level. We have also calculated polarization values for few pure transitions. So this work, I would like to acknowledge this. This work was a part of the project funded by UECTI CSR Kolkata Center. I would like to sincerely thank them for their assistance. Additionally, I would like to express my gratitude to VCC Cyclotron staff. Also, I would like to thank Young Physicist Meet 2023 committee members at Namas University for providing me a platform to present my work. Thank you.
Thank you, Mr. Piyush, for the
I think
yeah, Dr. Dhara, please continue.
he's not audible, maybe.
No, he was audible.
Piyush, okay, yes, it was audible. At this moment, Piyush,
yes, ma'am.
thank you so much. Okay, thank you so much. It was nice presentation.
Thank you, ma'am.
So from participants, if you have any questions, please you may ask Piyush directly. Probably there is no question. So just one query, Piyush. So what is your plan? What you will do with this 197 Mercury nucleus? Any application you want to show?
Actually, ma'am, this is the exact question every nuclear structure people afraid to answer. The thing is, there is no direct application. We are contributing to a large data set. There is a huge number of radioactive isotopes we have developed in our lab and studied the structure, and through which we are actually answering the bigger questions: the true structure of the nucleus, how they behave, what they are made of, how they function, and higher questions like that. So currently at this moment, there is actually no direct application, no humanity-based application for this work. But yeah, we are contributing in a large data set.
Okay, understood. So I think this is the starting of your research career. So you will find answer very soon. I hope so. So over to you, Purvadi. If you want to conclude, please conclude because it's already we are at the end of the session.
Yes, so we are at the end of the session. So in total, we have 7 talks. All of them are really very good one. And we wish all of them a good luck for their future. And maybe then we can finish this session. Do you want to say anything, Dr. Dhara? Or maybe Dr. Niyogi, Dr. Das, do you want to say something?
Yeah, just information that already the course session attendance links are in chat box. So participants, please fill it up. And tomorrow we have very interesting session all the day. So please, all of you should join. It's very necessary, and maybe you have finished your presentation today, but don't plan to be absent tomorrow, please be please all of you should be tomorrow with us. This is the message for all of the participants here.
Okay, so let's say goodbye for today, and let's once again meet tomorrow morning with a new presentation. See you all tomorrow.
Thank you.
Thank you.
Thank you so much. Thank you so much. Yeah, Shomendranath Shaha, all feedback links are available in chat box. I have already shared.